Um, well, good afternoon, everyone. My name is Alfred Spormann, and I'm the director of the Novo Nordisk Foundation CO2 Research Center. And I very welcome you all today for the second Carbon Forum. The Carbon Forum is actually an idea that we developed in the center early on when we realized in order to have an impact, and I should say CORC is a mission-oriented center at the interface of chemistry and life sciences to develop new science and early technologies for carbon capture that works at scale. So with this in mind, we realized very early on when we started the center that it's not only the science that will solve the problem, we need actually the entire ecosystem. And the entire ecosystem is not only academics, but also industry, it's government, policymakers, it's the public journalisms, it's the industry, and the capital. And we need to know, basically, to have an ecosystem with all of them, because for the science, it is important to know how the other entities think and what their constraints are for a rapid transition. And for the other entities, it's important to know what the science actually can do. So we need really a global and holistic view of the entire problem. And I should say it's a totally exciting time to start and be part of the green transition, because there will be an enormous amount of good things are going to happen, and it's a creative time and very exciting. But we need a holistic view. And for that, we decided we actually need to convey opinion leaders, not only from the sciences, but from all other fields, to come together, talk to each other in a language that we can understand and create ideas. We are not creating solutions here, but we are catalysts. The center knows what good catalysis is. That's our bread and butter. So we want to be also a catalyst to accelerate the green transition by including the different stakeholders. So today we have actually Marta's idea. Marta is a professor in Aarhus University and a CORC PI. And today's theme on technology learning for the green transition really came from you, and you developed this idea. So what the hell were you thinking when you had this idea, and how did you go about putting this program together?
So I would say, thank you, Alfred. I would say I was not the only one. We were having a conversation and a common thinking. But the idea is that at CORC, we are well aware that we have a big challenge ahead of us, and that it's important to reach, let's say, mid-century with some technological solutions that can help us fight, mitigate climate change, and even compensate for some of the emissions. And one important thing is that we need to go quick. So speed here is important because we need the solutions in the next few decades. And then we start thinking about how can we incorporate in our thinking as researchers, but also in the design of policies, this concept of speed. How can we make technologies learn faster? And then in our conversation, we were saying, well, why not looking at other examples? Why not looking at other technologies that have actually developed pretty fast? Why not looking at other regions in the world where they are trying different approaches to help the learning? And why don't reflecting all together in this kind of ecosystem on this idea of how we help technologies develop fast and in time. So I think this is a little bit the background of this session.
No, awesome. And I think you assembled an awesome team of opinion leaders. Just for my personal thing, what is the best outcome that you want to have from this day?
Yeah, that's a difficult one. I would say for me, one of the good outcomes will be that some of us have learned something, and that this kind of system thinking is embedded in our minds, so it's helping us reflect and prepare for the next step. So everything that we are doing, either being communicating or doing research on a technology or doing system thinking, is kind of reinforced by the discussion and the conversation that we are having today.
Yeah, great. So let's do some system thinking, and we welcome Nina on stage, who will actually shepherd you and actually give a shape and form to the different discussions and panel discussions that we have. So thanks for coming.
Well, thank you very much, Alfred and Martha, and welcome to all of you, and good afternoon here in the old stock exchange in Copenhagen. I am rather thrilled about this venue. It used to be the stock exchange for 200 years, built in 1620. And then it was a pivot for Danish trade, or Copenhagen trade, for nearly 200 years. And I guess the topic we are to discuss today may reach 200 years into the future as well. And we are to discuss, as Alfred and Martha said, how to accelerate the green transition and discuss the role that carbon will play in the future. The old stock exchange is currently being renovated. That is a process that is going on for years because it's an old building. So we may have to put up with a bit of noise coming from the outside. We'll just have to live with that. As Alfred said, I'm Lønnebjerg Christensen, and I'm going to take us through the next 5 hours of really, really interesting keynotes and panel debates. We have quite some time for questions coming from the audience. So if you take your phone and put them towards the QR code, if we're lucky, we have a QR code here. Otherwise, there's a QR code in the program on your table. You can see the full, excuse me, you can see the full program there, and you can also see the QR codes. There's one code for today's program, and there's another one for questions on Slido. So if you scan that code, it's going to take you to Slido, and you can post questions and comments to me. And that goes for all our viewers with us online. We have quite a few people joining us online, so a very warm welcome to you too. You can join us posting questions and comments as well, so please let all these things flow. I know there's a lot of competent people in this room, and that goes for you online as well. So please join me in asking questions to all the panelists. I have another really exciting thing to show you, or to introduce you to, and that is our graphic facilitator, Anna Leiborn. Anna, please come and join me here on stage, because some of you may have met Anna during the first minutes of the conference or during your registration. Anna is our graphic facilitator, and she has the humble task of trying to draw what's going on here on stage, which is quite, I think, a task for you. But Anna, you spoke to the participants during registration about, what they expected from today. What did they say?
Well, we have a lot of expectations in this room. So just going over them quickly is a lot of people are very eager for new knowledge. So what is moving in the carbon landscape? Some hope for new collaborations. So remember to talk to each other.
Yeah, network.
Share insights. What is sustainable carbon balance? How can we balance things? Insights on which handles will make a difference out there when you scale it. Understanding the challenges related to safety of the people regarding new technology. Hearing input about carbon removal from both sides. It could be from multiple sides. Scalability was a big thing. So how can we scale things? Because we need to move fast.
Yes.
And something concrete that can be scalable. There was also a reflection about the changes within technologically and regulation and different expectations from many sides. How can we communicate in policy and have communities supporting technologies, and we need to communicate in a way where people understanding and can take actions. This table is a bit in the way for some of you, but it's also very small, but it will be standing over here so that you can see it afterwards. Then we have a note about wind technology. It took about 40 years. Now we're in a big crisis, and we need to accelerate a solution quickly. We have, 5, 7, 10 years to find a solution and to have society to accept that solution and have it implemented in a scalable way. what comes first? What moves after the other? Does science follow politics, or should politics follow science? And newest ideas. People hope to hear the newest ideas today in this very room. And then there was a big cloud coming around it with the systems thinking, couldn't it be nice if we could put all this together in a big system and get some action out of it?
Okay, Anna, but that's excellent. It's quite a lot of expectations. Hopefully we'll fulfill some of them here on stage. Anyway, you're going to join us all day. You will draw throughout the breaks, and you will join us for the last panel debate, do a live drawing of the panel debate, and then we'll have a quick wrap in the end of the conference. So, and I guess these posters will be outside, right? So everybody can come and enjoy them during the breaks, and maybe add a bit here and there. So, but thank you very much, Anna. Great to have you here. I'm looking forward to the result anyway.
Thank you.
Good. Yeah, so I think that's pretty much it for me. Now, as I said, the program is on your tables, but you can also scan the code and get it online. I think I would like to introduce today's first keynote. He is coming from the US, and he's going to speak about roads to CO2 removal in the US. As you all know, the US has a pretty interesting road to CO2 removal at the moment, which is something I guess most countries can learn from. And Roger Ains is our next speaker. He is Senior Advisor for CO2 removal at the US Department of Energy and also Energy Program Chief Scientist at the Lawrence Livermore National Laboratory. And he will be speaking for a few minutes, and then he'll be happy to take questions. He'll speak for about, I think, 25 minutes or so, and be happy to take your questions afterwards. So everybody, a warm welcome to the Old Stock Exchange, and Roger, the floor is yours.
Thank you. I'm delighted to be in one of my favorite cities and one of my favorite countries. I'm glad to see you all here, and what a beautiful building. I'm going to talk today about something that we don't talk about in CDR very often, that is the supply curve. How much is out there, and how much is it going to cost? As much as we can estimate it today. Now, you all have seen this kind of graph many times before. It basically says we need to work very hard to eliminate as much of our emissions as we possibly can. That's the biggest task. That's the primary task. It's the most important task. But when we run the math, we find that it's not going to be enough to get us to net zero, which is currently our best estimate of how we're going to hit temperature targets that we would like to achieve. So we have to reduce emissions using negative emissions. We have a positive number, we add a negative number to it, we get zero. We'll also have to remove carbon dioxide that's already in the air. We've already put too much, and we're going to continue putting too much in there. And so that's the focus of my research. The focus of my job at the Department of Energy is to understand how to prepare for those negative emissions, recognizing that we have this other thing we have to do first, and we can't let the negative emissions effort interfere with our stopping emitting carbon pollution into the air. So we've thought about what we're going to need in the United States to do this. And same kind of color scheme as in the graph I just showed you. Those are blue bars are our targets that we have in the United States. And we want to hit net neutral in 2050. Well, there's a large range of numbers of how much we're going to have to subtract in 2050 to hit zero. Why is there such a big range between 500 and 1,500 million tons a year? Because we're not sure how all those other things are going to work. And there are people who are optimistic and think that we're going to get there really well. In fact, there are people optimistic and think we won't need negative emissions at all. I'm not that optimistic. 500 million tons is about the minimum. That's the most optimistic number that I'll tolerate at the moment. But frankly, we're not doing very well. We're not on track to hit that 500 million tons, and we may need more, we may need 1,500 million. The good news is, as far as policy goes, those are both large numbers. Anything that gives us 500 million can easily give us 1,500 million, and we can make those decisions along the way. So we don't need to know now exactly how much we need. So at my laboratory, Lawrence Livermore, we've been thinking about this kind of supply curve problem for a while. We started in California when California's worked on this for a long time and knew exactly what its current programs were going to yield, and the answer was it wasn't going to get there. Wouldn't hit net zero. And so we wrote a report describing how California could use negative emissions to achieve net zero. Very influential. The state now has a world-leading CDR program. A bunch of projects are up and running. They recognize that that's an important part of their future portfolio. We then helped Microsoft Corporation understand what would be available in 2030. They have a very aggressive net zero goal at Microsoft. They want to meet it in 2030, but they're also interested in helping all other corporations. What kind of assets are available to use by 2030 and how much would they cost? Now, we've begun what I think is really an almost finished, the important job of what's the nation, what does the United States need to reach its goal? But rather than phrasing it as need, what's available? What could we do if we chose to across the United States? So, the important part of this slide is these results are embargoed. Please don't share these until December 6th. I apologize for that. The report was supposed to come out yesterday. We got a little behind. So, I'm sharing it with you. I'm delighted to share it with you online, but please do not share it further until December 6th. So, we set out to do a very high-resolution piece of work. What we discovered is when you do country-level assessments, you average out all the interesting stuff. So we go down to the county level, which I understand is called the commune level here in Denmark. Very similar political boundary. And very similar kinds of changes. You have a giant commune here of Copenhagen. You have small agricultural communes. That's the same problem we have in the United States, but it's also the same opportunity. They have very different things they can do. We want to understand the capacity and cost for durable, measurable, and additional removals. You don't get to count stuff that's already happening. You have to add new energy to do it. It all has to be additional. We're taking into account other important factors for which, in the United States, environmental justice is a huge one. Land use, it turns out, of course, the bottom line in this report, land use is the most important thing you're going to run into. Energy, transportation. But most importantly, this is not a policy recommendation. This is simply an assessment of what the opportunities are. Policymakers can then take this at a national level, at a state level, or even at a city level. A small group can take this and say, this is what we would like to do, and then make their own policy determinations. In order to get there, we had to assemble a national team of experts. We went across the entire country, grabbed a bunch of people to do this, a bunch of national labs, a bunch of universities, and I got to tell you, look at all the smiles in this picture. This was fun. This was hard work for 2 years. It's really hard work right now. I'm here talking about it. Everybody at home is scribbling and finishing the final document. But this is a really enjoyable thing to really have this kind of impact and look at the problems, not just about a single technology, but how does everything fit together? How do you get along with the other 29 people in this picture? Well, another figure that I hope you've seen, which is all the various ways you can remove carbon from the air. The various technologies across the top, and then across the bottom, the timeline on which those operate. And when we say durable, we tend to think about longer timelines, but we recognize that some of the things that have short timelines, decades, can be made durable by simply repeating them, which for many of the soil and forestry solutions is what you'll have to do. So we looked at all of these things and said, which of these apply to the United States? Which ones do we have enough information to understand right now to make a good a reliable estimate of what's available in the future. And unfortunately, many of these are new. And many of you will be hearing from Harry later, who's talking about ocean capture. Didn't make the list because we didn't have enough information when we started 2 years ago. Might make the list today, but certainly there'll be another one coming in which we will include these other things. But for the moment, we did not consider all of those things. And so the minimum is we had to think that you could get 10 million tons of capacity from that technology in order to be included in this report. We ended up with 5 core issues. 4 of them are technologies, and one of them is a storage method. Forests and soils, you're probably familiar with this. These we often call these natural solutions. I tend to think of them as where the carbon is stored in an ecosystem rather than something else. But and then 2 techniques that we think of as more on the engineered side, but really the issue for them is that the storage is underground, is in geologic storage, similar to what has held oil for many years. You compress CO2, put it back underground, turns into a liquid, it stays in the same rocks that held oil. And as effectively as oil is our current belief. So we end up with these 5 major technologies which have to share resources and land and energy. You can't double count. You can't imagine that there's some magical source of any of those things that's going to make as much as you want. There isn't. It ultimately land. It's always land. There's not enough land. And we asked of those some key questions. What are the feedstocks that it takes to do that job? What is the material that goes into the process? How much land does it use? Where does it get its energy? And we required that energy be additional. That means you'd have to build new energy to do it. The United States does not have a decarbonized electric grid today. You can't take electricity off the grid and steal it from somebody else who's trying to decarbonize that grid. That's the highest priority activity. So if you want to build a direct air capture plant, you would have to plan to build additional energy to power it. And because it's difficult to build transmission, we required that additional energy be local. In this case, in the same county, in the same commune. That's because that's how our geographic data worked. But, that just make it local so you don't have to build big transmission lines. You had to have available storage of the CO2. As many people in CORC are working on turning CO2 into important products. That is a terrific goal. Absolutely, we should stop using oil to do that, but it's not enough for all the CO2 that we need to store. We need additional storage. And finally, we have to transport either the feedstock or the CO2. So, spoiler before I walk you through how we do all these things. What are the cumulative results that we got? The first 2, green and yellow, are the so-called natural solutions. This is how much total we could get by 2050. And it's a couple of billion tons. These are real, these are large numbers. And then on the right, for our 2 more engineered approaches, biomass and direct air capture, similar size numbers. So what we found is, if we look at the integrated impact over the next 30 years, all 4 of these are about the same. Good news. We need to start on all of them. We need them all. We do not need them fighting among each other. That's not good for us. We need to get going. If we look at the rate that we're going to have, that's different because we can start our natural solutions, our soil and our forest management today. There's nothing stopping us. We don't have capital constraints. Farmers, foresters know what they're doing. We just need the systems in place to pay for that. And when we do, we're going to be fine with that. The other 2 engineered methods are going to spin up near the end, near 2050, because there's an enormous amount to build. There's a lot of infrastructure. There's still development to do. We know how to do these, but we don't do them at large scale yet. But once they spin up, their rates will be very large. And this is one supply curve that you can get from doing that. And I'll walk you through in the rest of the talk sort of what the components of this are. But here's the natural solutions, soil and forestry over here, relatively small rates. This is the rate per year in 2050. And then biomass-based methods, what can we do with waste biomass in the middle, and direct air capture on the right, in order of cost. So presumably you would look at, this is the supply curve, this is the order in which you would choose these things. That actually turns out to be not all that significant. People have other reasons that they choose things, but it's one way to present the results. Let's walk through some of the details of some of these things. Improving how we manage our forests is easy, low-hanging fruit. Turns out it's not a giant change in the United States, because remember, it has to be additional. If we're already managing the forest, well, we don't get to count that. That's not new, it's not additional. So, we looked at 3 important forest regions in the United States. They have very different characteristics. Northeast, not challenged by fire, not really used a lot commercially. The Southeast, heavily used commercially. All the Southeast forests are in private hands. These are people's farms. These are their livelihoods. And you can't say, oh, we should just let those grow. No, that's their livelihood. We have to let them do their work. And in the West, forests are principally owned by government. And so there's a different set of challenges there. And what we found in the West, you can get a significant amount of improvement by managing the forest mainly for fire control. Keep the forest from burning is the most important thing you can do in the West. In the East, in the Northeast, those forests can be managed better. They've actually been allowed to grow back in ways that aren't optimum. You can better manage the forests so that they have optimum tree growth, and you can use some of those forest products for things like timber for 1600, it works. You can use it for long-term storage. Big hitter, though, in the U.S. is the Southeast, where there's a lot, the pine forests grow fast, and there's a lot of places where you could grow new pine forests down there, and that adds up your carbon total in a big hurry. So different strategies for the different regions of the United States. How we manage our soils. I am a big fan of soil carbon. We have a huge program in soil carbon at Livermore. Why? Because the target is so gigantic. We could put so much carbon back into soils that we've lost. And the question is, how do we do that? And we focused on agricultural soils because you manage those soils, you have people who are responsible for them, you have people who know how to handle those things, as opposed to imagining you're going to do something on pasture lands or something, which is much harder. And the 3 things that we looked at here are cover crops, that's really important, perennial carbon crops, changing the crop you grow from something like corn that has roots that are only this deep, terrible for putting carbon deep into the soil, it doesn't reach there. If you had perennial crops like the grasses that made the great soils of the central United States, those had roots that went down 3 or 4 meters. Is there an opportunity to replace some of the shallow-rooted things with deeply rooted things again? That's a great win if you can do it. And finally, field borders. There are edges of fields which are basically not used today, in which you could change the things that are grown there, which is also good for biodiversity. Perennials, local crops, butterflies like those. That's a good answer. And so this is a bar chart of where you can do those things. And this gives you a sense of the scale. This is every county in the United States and the total impact they could have. And you're going to see one funny thing up there. You see cover crops are really important in a few counties and then not present in neighboring counties. Why is that? Usually because it's already being done in the neighboring county and it wouldn't be additional, don't get to count it. But cover crops are really important because you basically keep carbon from being lost, but you add carbon by having plants growing all year. Then if you could add carbon crops, that would be great. Now let's look at the 2 engineered approaches. Direct air capture. Where's Jan? Picture of his plant. Climeworks. You're going to hear from him. Very picturesque plant. And what we call bikers. Why do we call biomass methods biomass with carbon removal and storage instead of BECCS, biomass energy with carbon storage? The important thing here is removing the carbon, not making energy. We don't run our economy on wood today because it's a crappy energy source. But it's a great carbon source. Biomass is half carbon by weight. So we should focus on the carbon removal, and if we get energy out of it, that's terrific. But the real focus is getting the carbon out of it. So I'm going to talk about these 2 methods together because they share many of the same constraints. And the biggest constraint they have is land use. In the United States, we have incredibly detailed maps of how land, what land there is, what soil, what it's being used for. Is it a farm? Is it a playground? Is it a forest? We know that to things the scale of this room. And that's true of almost every developed economy around the world. And you can look at that then and you can say, what are the different categories? What are the things that we can and can't use for these approaches? So if it's protected versions, which is for us is things like parkland, okay? Or cities. You can't use a city for this. You have to take those out of the equation. So this, as we move across, we keep removing land from consideration. And you get to things like all wetlands. All wetlands are off the table. Can't use them. If there's existing infrastructure on it, if it's an airport, you can't use that. And then you have an interesting category here, and that's all the things that are needed to create energy to decarbonize the grid. So all that first category, all the remediation that we need to do to stop emitting carbon, that you can't use either. You can't eat into the land that's required for photovoltaics to decarbonize the grid. So that ends up, and turns out there's actually quite a bit of land that's available but not required for the purpose. That's the good news. And you end up at the end with the amount of land required for these two methods, biomass and direct air capture. And you will hear people lament how much land these things will need. Yes, it's an enormous amount of land, but it's a tiny fraction of what's available. All depends on your perspective. A really key thing in the United States, though, is where is the storage? And this is the thing that Denmark is doing such a great job of looking at right now, is where is the storage? Because transportation is so difficult. If you put your new projects on top of good storage, they're just going to go faster. And for the United States, that good storage is almost all in the Gulf Coast. And you'll notice that the Department of Energy's two big new projects to do direct air capture, billion-dollar investments are in that green zone down there. There's other places around the country that are good, particularly going up here in this corridor, which is also the corridor where all the great wind power is in the United States. There's good storage there, and in my state, in California. There will not be storage underneath Washington, D.C., even no matter how good the geology is. That's not going to happen soon. So we take all these things and we put them together into a map like this. We say, where can you build direct air capture? This is using the technology options for the two major methods, the kind Climeworks does and the kind Carbon Engineering does. So a solid sorbent and a liquid solvent approach. They have some differences in how they conduct their operations. And boy, the geographic sensitivity is pretty big, isn't it? Just most of the country is off the table, but there is this great band where it makes sense, where you can make local renewable energy, where you have geologic storage, and you have enough land to do all of those things. If you're building a direct air capture plant, the land to do the capture is trivial. It's the land to supply the energy that takes a lot of land. So, this is good. And our hope is that people in all those counties will look at that and say, that's my county. I'd like to see a direct air capture plant here. I'll go and talk to those companies. Instead of the vice versa, which happens, which is a company comes to the county and says, we want to build a plant here, and everybody's like, I don't know what you're talking about. Hopefully this is a better approach. I want to spend a few minutes on biomass because it turns out to be such a big part of our analysis. These are all the different kinds of biomass and the kinds of elements that you have to consider. Biomass is incredibly complicated when you try to analyze this. There's a lot of different sources. I'm not going to spend a bunch of time on this. You can wait till December 6th and you can read the report. But all of these sources could be considered, and the most important of them are that I not make noise with my microphone. Oh, well, that solved that problem. Okay. And all of these, the first thing you want to think about is the waste sources. because you don't want to make new biomass. You don't want to cut down trees you weren't going to cut anyway. You want to use waste, and it turns out there's an enormous amount of that. And we analyzed all the different ways that you can use that and get the carbon out of it, most of which also remove some energy or a useful product because that helps keep the price down, right? This is the win-win of biomass. And when we look at just waste biomass in the United States, which turns out to be almost 500 million bone-dry tons, so this is dry wood or dry trash, which would equate to almost 1 billion tons of carbon dioxide, right, when you process it. We find it's available all over the country. We have biogas, we have all kinds of agricultural sources, you have the cities where trash is important, and this is a huge number. People will talk about using crops to do this. That's fine, and maybe crops make sense in the future, but right now, this is easy. We can do this right now and collect the trash, collect the almond shells. Do you know that in California, we have 1 million tons of almond shells a year? Thank you for eating our almonds, but that's trash, and that's full of carbon, and it can be part of this equation. The next thing to think is a politically sensitive topic in the United States. We put 10% ethanol in our gasoline today. We use 14 million acres of prime farmland to grow the corn to make that ethanol. What happens when we electrify our entire fleet and we don't need that ethanol anymore? What happens to that 14 million acres? Now, this is the best farmland in the world. You're not going to immediately start growing switchgrass on it. But it's now available in a cascade, a domino theory of good land that's available to grow other things. And that adds a lot of carbon to it because with that amount of land, you can do things like you can grow switchgrass without changing the price of food because you have new land available to do it. Now, this is not a choice that is absolutely going to happen because you might choose to use that ethanol to make jet fuel. Okay, that's important too. But you can't make carbon negative jet fuel with ethanol. It still ends up being quite carbon positive. The last thing that I'm not going to talk about is if you decided to grow crops for the purpose of creating carbon crops, you could get almost 1 billion tons doing that, but it would impact the price of food. And there are some people who say 10 to 20% is trivial. I don't say that. I think those first two categories are great places to start, and if we still need more, we can have a discussion about it decades from now. And what does this mean in terms of just the biomass supply curve? All the different methods that I showed you, the 27 different methods have different colors here, but the important one is the orange one, which is converting that biomass into hydrogen. So you get all the energy out as hydrogen, which is valuable, and you get all the CO2 out to put underground, so you get the maximum footprint. And today we believe the price for that is very low. It's all underneath the United States target of $100 a ton. That's pretty important. Now, this is giant infrastructure, a supply chain that's unimaginably large. It's not trivial to do this, but the goal is good, and we think this is a really important part of the United States' future. And let's come back to this question of synthetic aviation fuel, or sustainable. I'm sorry, I always call it synthetic. It makes a big difference in that original supply curve. If you said, we're going to use all of that biomass, all that 500 million tons, just to remove carbon from the air, then the total for the entire system is only $87 billion a year because the biomass is less expensive than the small amount of direct air capture you would need. This is to reach 1 billion tons, and we might need a lot more than that, in which case you just keep adding more direct capture. But if you use half of that, or if you use all of that biomass to optimize to make jet fuel, you have a much more expensive system, but you've made all your jet fuel. So this is a decision that policymakers very well could make, and this is not up to me. We just supply the numbers and let people use them as they best can. But this is the kind of trade-off that you face in doing these kinds of analyses. Furthermore, we really think hard about what is going on with environmental justice and how you can make communities more aware of the positives and negatives of doing these things. We think it's perfectly reasonable for we scientists to make it clear that both of those occur. Companies tend to come in and go, oh, great for you. Well, no, maybe it's not. And at the same time, communities should be making decisions about what kinds of things they want to bring to the table. The answer, in the end, is that every one of these methods can contribute. Almost the entire country can contribute. Any community, any region, any state in the United States has removal options that make sense, that are not too expensive, and that are good for the community and good for the environment. This is a thing that is a win-win and that communities can choose to do. Let me finish by saying that that's the most important thing. We need to keep everything in play. We need them all, and we need to let people choose. We need to put enough information in the hands of people like you, people in these communities, activist groups, people who care deeply about the future. What does this mean? How can they achieve the goals that they want to have? How can we all have the world that we want to live in the future? Thank you.
Well, thank you, Roger. We've had quite a few interesting questions, so I guess I'm just going to go through them, and I'll look forward to your answers. And you're going to join us for the following panel debate. Yes. So, I mean, there may be a few questions that we don't have time for now, but I'll save them for later then. Roger, what are the best ways to measure soil carbon and its changes over time and depth, reliability and affordability?
I'm sorry, say again.
Yeah. What are the best ways to measure soil carbon?
Measuring soil carbon. It turns out that a lot of people are excited about measuring carbon from satellites and from airplanes. The best way today is still just dig it up. It's not hard to do, and it's a well-known method. And great, you can come up with easier ways to do it. But just taking a core and digging into the ground is still the best way to measure it.
CORC just hosted a talk by Eli Jablonovic on dry storage of biomass, bird plastic bags. What do you think of this idea?
I'm getting so much echo up here, I'm having trouble. Oh, that's great, right there. Dry storage of biomass. The challenge there is that the biomass may turn into methane, as we find in our landfills. And so people have lots of methods that they think are going to stop that from happening. And the only way to know is that we have to test that. And I won't have an opinion until we do some more tests and see how well that works. Because if it turns into methane, that's bad.
Roger, later today we're going to discuss social acceptance. And from what I can tell, this includes a lot of social acceptance. What you suggest, I mean, changing, for instance, farmers' crops. How do they react to that? Are they willing to embark on this journey, or what does the societal acceptance look like in the US when we're going through these changes? I'm aware it's very different.
There is not much knowledge about these things. If I got a group of farmers in the Central Valley together in a room like this, most of them would not know anything about this. And so they don't have an opinion. What happens is we have various pressure groups either saying this is a great idea or this is a terrible idea. And those pressure groups tend to be pushing the conversation rather than knowledge. We're hoping to increase that. And that's one of the things that Holly Buck is great at. And so I'm looking forward to her talk today.
Yeah. Okay. Well, Roger, that's what we have time for now, but luckily I'll see you later joining us for the debate. So thanks for now.
All right, thank you.
Yes, our next speaker is, you already met her, Marta Victoria, CORC PI and Associate Professor of Modeling of Large-Scale Energy Systems at Aarhus University. And Marta is also joining us later for the debate, but for now she'll speak about how technology learns. So Marta, the floor is yours.
Thank you. Thank you everyone for joining today. I want to focus on this presentation trying to answer this, in principle, simple question of how does technology learn. And to do that, I want to cover three main ideas. First, I want to review the experience of a technology that has learned really fast, and that is solar photovoltaics. Hopefully, there are some lessons learned that we can grab from that technology. Then I want to discuss what I do as a researcher, which is system modeling, and how do we include technological learnings in our systems. And finally, I want to give some back-of-the-envelope calculation of what this would mean for technologies capturing and converting CO2. So let's get started with the history of PV. I would like to start showing this figure, which is quite famous, I would say. You could see here the prediction of capacity of solar photovoltaics. This was published by the International Energy Agency. Every year, this organization publishes a World Energy Outlook describing how they see the world evolving. So from 2006 to 2018, you can see the forecast of global PV solar photovoltaics capacity to be installed in the world. And then this black line represents what was actually installed in reality. So for 14 years, International Energy Agency was consistently underestimating the capacity of solar PV, and reality was saying, no, we're going to have actually more PV capacity. And this is by no means an attack to International Energy Agency. Almost everybody underestimated the potential for solar PV. This is just meant to be a reflection of sometimes it's really difficult to see big transitions coming in. And just to clarify, the most recent World Energy Outlook include almost an exponential growth of solar PV, and they declared that solar is now the cheapest technology to produce electricity in most part of the world. But let's keep going. It was not only the International Energy Agency. There have been many models which has been forecasting the cost of solar in a wrong way. So you can see here many integrated assessment models which are used to create the scenarios in the IPCC report. In black, you can see the cost estimation for solar PV for future years. And then all of these are the model assumptions. And then what you can see here for 2020 is the cost that the technology achieved actually in 2020. This is the average cost. This is the cheapest cost in the world. So many models assumed higher cost for solar PV in 2050 than the technology has already achieved in 2020. And then, of course, they don't see solar playing a big role in future any year scenarios. So how is that everyone got it so wrong? Actually, what happened is that solar changed really, really fast. From 10 years, from 2009 to 2019, solar photovoltaics went from being the most expensive way of producing electricity to the cheapest way of producing electricity in most part of the world. And this just happened in 10 years. And this is why many kind of miss this quick transition. Let's try to go deeper into how is that this happened and how was it so fast. So I'm plotted here for the years that we have data. So let's say for 40 years, the price of a PV model, let me move here. The price of a PV model as a function of the cumulative capacity, all the capacity that we have installed worldwide. And I'm using a log scale. And when we do that, what we see is that we find these clearly linear relations. And now I want you to stop for a minute and think that there is no fundamental or physical reason why that justify that when we plot the cumulative capacity against the price and use a log scale, we should see a linear relations. There's no physics explaining that, but we can see that this has happened for 40 years. It's a good way would be to assume that this is going to keep doing. And why is that? What is that makes this happen? Well, this is known as learning by doing, and this just means that the cost of a technology decreases as cumulative capacity, as experience increases. We typically use this formula saying that the ratio between the cost is related to the ratio between the cumulative capacity in 2 time steps to the power of a certain value b, which is the slope in this curve. Actually, typically, instead of referring to the exponential b, we refer to the learning rate because it's an easier number to remember. And the learning rate is just a relative price reduction when capacity doubles. So So we just go to this formula, capacity doubles, so we put here a 2, and we have a way of calculating the learning rate. So for solar PV, the learning rate has been 23%. Every time the capacity has doubled, the price has reduced by 20%. And this is one of the things that makes this technology learn very fast. And we have seen this not only on solar PV, but many other energy technologies. Actually, the first time that we saw this was in 1936, in which that year Wright reported the same behavior for the aircraft industry. So we know this learning, even if it's not based on physical evidence, is something that is happening, and we can see that happening. Let's talk a little bit more, and before I keep going, technologies do not only learn by installing more capacity, but they also learn by research. So we can see technologies, particularly in the earlier stage, where the cost is related to the amount of investment in research. But let me talk a little bit more about solar PV. Why is that this technology learned so fast? Well, it has to do with the property that this technology is a modular technology, also a granular technology. And later, our speaker, Charlie Wilson, will be describing how this is key. So what do I mean when I say that? Well, if we think about a rooftop installation, maybe comprising 8 to 10 PV models, or we think about one of the largest existing PV park, Batla Solar Park, 2.2 gigawatts, equivalent to roughly 2 nuclear power plants. Both are using the same PV model. Just in this case, we're using millions of them. And of course, when you need to produce the same element and repeat that millions and millions times, there's a higher chances of higher opportunities for learning. In particular, for solar, we have had some drivers, such increasing efficiency, a massive scaling, and on automation of the manufacturing, strong competition between manufacturers, cost reduction in other system components, or reliability improvement. But all of this make this strong learning. Actually, during some part of the history, people start thinking, but are we going to keep learning forever? And around 2000, there was a lot of debate about, well, maybe learning has just stopped. What happened here is that before 2000, solar photovoltaics was using scrap silicon from the semiconductor or the microelectronics industry. It took some time to produce or to install new factories producing, purifying, and crystallizing silicon to be used for the solar industry. But as they were in place, the learning kept going. It's also interesting to realize that for the last 6-7 years, we have even seen an acceleration of learning, mainly because of different drivers, mostly due to a standardization of the supply chain and the cell design, the tools that we use to produce solar PV. I won't go into detail, but we can see that many different processes require solar PV, texturization, printing, diffusion. They have increased the throughput. So now we have the same machines, but we use them to produce more solar cells. So all these things together with an historical lab research. So the fact that the solar cells were also small allow many research worldwide to do their research, to have improvements on solar cells that were quickly transformed or translated into the industry. So all this is what kind of created this evolution of the technology. I want to mention a couple of few extra things that I think are relevant. One is there's also learning not on the hardware, but also on the software. They're learning on labor, regulation, permitting. We can also say that the learnings can be local or global. So it's not only about making solar panels very cheap, but also about setting in place, educating the workers that install them, setting in place the regulation, making the permitting fast enough. And to capture all of this, we cannot say, let's say we have a target for 2030, we cannot say, well, let's wait until the technology becomes cheaper around, and then the year later, in 2029, we will come in and install all the technology that we need. This kind of strategy was discussed a few years ago here in Denmark. It's also known as the hockey stick approach. And in my view, if you wait, if you don't do, you don't capture learning by doing. So you're not making the technologies cheaper. We can also think on our spillovers from other industries. What is something that other industries know how to do, and we accelerate and incorporate into our learning? And it's also super important to include policies that stimulate market growth. In other words, you need to be willing to pay a technology around here when it is more expensive than what it's going to get, to help the technology go through the whole learning. And we need to consider how are we going to help the new technologies learn now that they are expensive, so that they are ready when we need them in a couple of decades. All right, so enough for the PV history, because I want to also touch upon the other topics. How do we, and then the answer of why the International Energy Agency and other models were not seeing that is because they did not have a good representation of learning of that technology. So how are we working to include that better and to make our models better? Well, typically what I do as a researcher is that I work with these larger scale system models. We look for the cost-optimal system design, and this is a system involving many things, and we try to represent constraints to model physical or societal limitations. So to give you an example, let's say we want to minimize the system cost, including all the elements that we need, including generation, storage, transmission, but at the same time we want to make sure that in every time the energy generated and the balance is enough to supply the demand, and all of this is solved making sure that the sum of CO2 emissions is below a certain CO2 limit. To do that, we include a detailed accounting of all the carbon capture usage and storage. And when we do this kind of analysis, so far, and what is very typical, is to assume a certain cost and efficiency for now and for the future. We typically used cost assumptions for the Danish Energy Agency technology data catalog. And then we run our models, and of course, our models include millions of variables, but I'm just plotting here one variable to make it so that I'm able to make the plot. So typically, when we minimize the system cost, we find an optimal solution that minimizes this, and we can have, as I said, the physical or societal constraints binding, like here, that is affecting where is my minimum or not binding. But I can do that and I can solve these issues because I make the trick of making sure that all my equations are linear. And that ensures, roughly speaking, that I'm going to have a linear problem, so with just one solution. However, learning, as I just presented in a few slides ago, is not linear. There's some exponent going on there. So what's happening when we include learning in our model? Well, we don't have anymore a nice, convex, optimal solutions, but we find several minima, which means now it's more complicated to get to this minima. And this has some complexity from the point of view of how we handle and we optimize the model, but it's also some implications that I will describe in a minute. So what we do is, using these equations, but also a detailed representation of Europe. So we have the different countries in Europe, potential of wind and solar and how they are interconnected. We reach to resolution close to the NUTS 3 or county level. We also have a detailed description of where do we have the different industries in Europe today, and when they change, what does this mean for the model? We also have representation of where we have potential to store CO2 underground. We put all of this together, and we solve the optimization problem. And very recently, we have published a paper doing that, but at the same time, including learning. So making the system nonlinear and including that some technologies can learn. What we did is to start by including learning on solar, wind, and electrolysis, including the learning rate based on historical experience, and also capture a little bit this local and global learning dynamics based on the ratio of the capacities installed in Europe. And with that, try to understand better what could potentially happen with electrolysis. Because if you could see the cumulative capacity of alkaline electrolysis is quite low today. And what we learned is that we could potentially replicate some of the fast evolution that we have seen with PV. Actually, what we learned is that just using exogenous assumptions from the Danish Energy Agency, we expect to have this kind of evolution. But if we include learning, and we include an ambition carbon budget, we could have a different evolution on the cost of electrolyzers. So we are trying to push forward the state of the art and try to learn better how to include this modeling of learning within our models. Exactly. So this is kind of the technical part that we are doing, but I also want to reflect a little more about what does this mean? What does this mean that I say when we include linear, it makes the solution when we include learning, in the model, it makes the solution non-linear, and then I have multiple solutions. What does it mean, this kind of solution space? Well, it means that in reality, what is going to be the optimal combination of technologies that we get in the future? So let's say if now I'm plotting the system cost, potential possibilities in this axis, but also how system evolves with time. What it means is that the optimal solution that I found, let's say in 2050 or at the end of the century, is not independent of what happened before. So there's a path dependence. We have the possibility to tune, we have the possibility to help foster the learning in some of the technologies so that they are ready when we reach mid-century. So the solution is not as simple as we have thought. We have, as I said, a possibility of helping some of the technologies and end up with different solutions. That's kind of what we are investigating, but from a point of view, this is also very relevant from a policy point of view. We could tune the solutions as we need it. Right. And then, finally, what I want to do before concluding this is to put some numbers and make some quick back-of-the-envelope calculation of what could learning potentially mean for a technology like direct capture. And this is by no means exact calculation. This is a way of helping think, and some results prepared by Sina Calwait. So the idea is to think this way. Where are we today? Well, today we have a cumulative capacity for direct capture of around 10,000 tons of CO2 per year, 0.01 megatons. This is where we are today. And we pay them at around 1,000 euros per ton of CO2. And there's a slight differences, but this is kind of a good reference coming from the IEA and this report on the state of carbon removal. So where do we want to reach? Where ideally we want to reach to some level of price that is competitive, around 100 euros per ton of CO2. And how can we reach there? We can follow many different paths. And again, I'm using this log-log plot to try to represent the learning that could experience that technology. So let me give you these two examples. On the one hand, we could learn fast. So we could have a 15% learning rate. This is plotted here in orange. And that will mean that when do we achieve 100 euros per ton of CO2? When do we reach this level? Well, we will need to have a cumulative capacity of 185 megatons of CO2 per year. However, if we have learning slower, if we start here, our ambition is also to reach to 100 euros per ton of CO2. With a low learning of 10%, we will need to reach a cumulative capacity of 37,000 million-tons of CO2 per year. I'm not saying that we're going to do one thing or the other, but I'm just trying to emphasize here the learning is important to take us one or the other direction. And how much money do we need to invest? So if you think about this curve, the total investments are just the area beneath the curve. So if we just integrate all this red, orange area and blue area, we can compare the two things. With a 15% learning rate, we will need 24,000 million euros through the whole learning process to get here. If we are learning slower, we will need much more money, so 4.5 millions of 4.5 European billions of euros. And can we do that fast enough? So if we need to reach these different cumulative capacities, well, let's assume an annual growth rate of 25%, which is very ambitious, but we have also seen that growth rate with solar PV. How many years will it take us to get to these final solutions? So with the first option, we need around 36 years. We could roughly do it by mid-century. With the second option, we need around 60 years. So again, my objective here is not to say we are going to have either 15% or 10% learning rate, but more to highlight the idea that learning dictates what kind of future we could have and if we can get to a solution on time. So together with some of the other presentations that we are going to hear today, I think my point would be, let's try to identify technologies that can learn fast, that can get high rates of CO2 capture fast enough to be part of the solutions when we need them. And with this, I will stop here, and I would like to thank you again for your attention.
Thank you, Marta. You're joining us for the following debate as well. And the topic of that debate is how we can learn, or other technologies can learn from your solar PV example. And actually, there's one question here related to that, so we may just begin there. Would you assume we can apply the insights about technology learning of PV to other technologies in the same way?
Can you repeat the initial
Yes,
part?
and you can read it here because it's really difficult to hear. Would you assume we can apply insights about technology learning of PV to other technologies in the same way?
Thank you. Well, I think there are learnings from PV that we can transpose to other technologies. One of them is one key in PV. One key why PV has learned so fast has been the fact that it's a granular technology, a modular technology. So if we think of solutions to capture or convert CO2 that do not consist on big installations, but more on very scattered small installations, I think we'll have more on this later. But I think there is evidence that these technologies learn faster. I would say other thing that we need to learn from the PV is that we went through years. And I remember well because I was doing a PhD on solar, so I was very sensitive to this kind of message. But we went through years where solar PV was very expensive, and everyone was criticizing all the programs supporting solar electricity in Germany, in Europe, and everyone was saying, it doesn't make sense. Why do we pay so much, such high electricity prices for solar? But it's also thanks to this visionary policymakers that now we have the technology chips. So we need also some kind of policymakers that wants to help technologies together.
Okay. So Marta, there's another question about learning. How do you define learning for technology? Is it the inverse relationship between capacity and price?
So officially, we could say that the learning is how much, the learning rate in particular is what is the cost reduction in your technology every time the cumulative capacity doubles. And it's related with this slope that I was saying. So it's a relation between cost reduction and experience measured through cumulative capacity.
Mm-hmm. There's another one asking, is there a rational way to choose a technology within which to stimulate learning?
I think when we look at different technologies, some of them show faster learning than others. Solar PV, I brought this as an example because it's the energy technology that has ever shown the fastest learning. So in my view, this is something we should try to imitate, or at least try to learn better why there's so much learning from
Okay. So Martin, we're going to continue this conversation after the break. We have another presentation, and then we're looking into some of these issues related to learning and what we can learn from the solar PV example. But thanks a lot, Marta Victoria, for now.
Thank you.
And now, ladies and gentlemen, I think we have a networking opportunity in the library 20 minutes from now till 1:30. And I think there will probably be some coffee for us now. Enjoy. Ladies and gentlemen, welcome back. Welcome back to another presentation and the panel debate. Our first guest after the break is joining us from the UK. Charlie Wilson is Professor of Energy and Climate Change and Energy Program Lead in the Environmental Change Institute at the University of Oxford. And on top of that, he is a Senior Research Scholar at the International Institute for Applied Systems Analysis. Charlie, welcome. The floor is yours.
Thank you. Yes, so it's very nice to be here, and my talk actually follows really nicely on from the concepts and evidence that Marta was introducing around solar and learning, but it kind of generalizes this story into a whole family of technologies which we think of as granular. So by granular technologies, what we mean are, like solar, technologies that have relatively small unit size, relatively low unit costs, and that are modular and divisible. And so they scale by replicating. So these are shown at the top. And on each side, you can go down this spectrum to what we call lumpy technologies at the other end of the continuum, which have large unit sizes, high unit costs, tend to be indivisible, and so they grow by getting bigger, by upscaling. So nuclear power on the left and jumbo jets on the right. And the research that we published a couple of years ago looked at a very wide range of technologies historically and found these benefits of granularity shown here on the left. So they deploy or diffuse more rapidly, they're less risky, they're less prone to cost overrun when being built, they learn more quickly, as we heard from Marta, they offer more efficiency gains, they're less susceptible to lock-in, which is a phenomenon I'll explain in a moment. They're also more widely distributed, they're more equitably accessible, and they create more net jobs. And all of these things are critical ingredients of what we need in the pathway towards net zero. So I'm obviously making a whole series of assertions that I don't necessarily expect you to believe right now, but I want to show you the evidence which we compiled to back this up. And I want to start with this story about deployment speeds. So I'm going to show you quite a few of these graphs. I just want to explain that on the x-axis, you have our measure of granularity, so here unit costs. And each dot on the graph is an energy technology which we've observed historically, a very wide and diverse set of different energy technologies. But the more granular ones are on the left, the more lumpy ones on the right. And on this particular graph, on the y-axis, we're showing something called the delta T, which is a measure of diffusion speed. Essentially, the longer the delta T, the longer it takes a technology to grow to a certain market share. So what you can see on this plot is that the more granular technologies on the left have shorter delta Ts, or they deploy or diffuse more rapidly. So examples in our historical data sets were energy-efficient light bulbs and a whole range of different appliances that are on the more granular end of the spectrum. And examples on the lumpy end of the spectrum include things like gas pipelines and refineries, where the adoption effort, if you like, is significantly higher than the more granular. So the second benefit of granularity is what Marta explained very nicely and in much more detail than I will go onto with respect to learning. So Marta talked about solar and other kind of more granular energy technologies for which we've seen rapid learning include wind. We've also seen it now with batteries and energy storage. The exemplar, actually, historically, of very rapid learning is microprocessors or microchips, where we see these very, very high learning rates observed historically. But more generally, you can see, again, that the more granular technologies on the left have higher learning rates than the more lumpy technologies on the right. And two particular lumpy technologies have actually shown evidence of negative learning historically. That is, as cumulative experience has grown, costs have actually risen. And so nuclear power, particularly in OECD countries, and also flue gas desulfurization for scrubbing sulfur oxides out of the combustion stacks of power plants, are technologies where learning has actually been negative. And this is because with the lumpy technologies, you just don't have these many, many different units and cycles of innovation on which to experiment and improve and learn. So the third benefit of granularity is that there are more energy efficiency potentials still remaining in the smaller, more granular technologies like heating systems, as opposed to industrial scale, lumpy technologies like blast furnaces. And we think this is a very simple explanation that historically there's just been less economic incentive for the smaller scale. Energy essentially is a smaller proportion of the input costs for these smaller scale granular technologies, which has meant that squeezing out more efficiency gains has not been as important historically. But it means that there's more potential now with the technologies on the table. These two graphs are both evidence pointing to lower lock-in risks with more granular technologies. So lock-in is a characteristic of complex technological system that essentially represents inertia or resistance to change. And there are many different reasons explaining lock-in. One of them is that if you have very long-lived infrastructure, which is costly to retire before the end of its life, that creates a stickiness or inertia to change. And a second reason is that in technological systems, you have a lot of interdependencies or complexities between component parts of that technological system, which again create inertia to change. To change one thing, you need to have a whole knock-on effect of other things to change. So these are two fairly crude measures of granularity in our sample. The middle graph shows that more granular technologies tend to have shorter lifetimes, so they cycle and can be substituted out more rapidly. And the right-hand graph shows that you tend to have more complexity or through interdependencies in the more lumpy technologies, like in this case, the jumbo jet. So more granular technologies are also less exposed to this risk of getting sort of stuck and become inert in technological system change. So a fifth benefit of granularity is that they're more widely accessible, they're more equitably distributed. This plot is showing something called the Gini coefficient, which is a measure of equality. So a Gini coefficient of 0 is perfect equality, and a Gini coefficient of 1 is perfect inequality. So we're showing here across a variety of different technologies and also infrastructures that the more granular the technology or infrastructure, the more widely accessible it is. And so in our sample, the most equitably distributed technology that we had was the mobile phone. And we think this is one of the most equitably distributed or more evenly accessible technology in history worldwide, compared to something which is a few orders of magnitude more costly at the unit level, the car, which over 70% of the global population still do not have access to. Another benefit, really important benefit of granularity, is job creation. Now here the data set is relatively thin. There aren't too many data points, as you can see. But in terms of solar, which is a good example, also energy efficiency, there's good evidence to show that more net jobs are created when you control for the amount of output and the lifetime of these facilities. More net jobs are created in the granular technologies than in the lumpy technologies like thermal power plants. And again, we think this is because of this sort of highly distributed nature of granular technology. So you have overall higher labor to capital ratios. And then finally, the final advantage of granularity is evidence actually from the US Department of Energy's investment portfolio in energy R&D, energy research and development, that the social returns on that public money spent on energy innovation are higher for more granular technologies. They have higher benefit cost ratios. And this is both in economic terms, so in terms of economic cost savings and productivity, but also in broader energy security and environmental terms. And actually in the US DOE's portfolio, I think it was analyzed over about a 25-30 year period, the highest yielding investment they made was in energy efficient lighting ballasts in terms of the social returns on that public money spent on innovation. And some of the lowest yielding public innovation investments that they made were on flue gas desulfurization and advanced turbine technology that you can see on the bottom right. So that was a sort of snapshot of the evidence then behind the assertions I made at the beginning about these benefits of granularity in terms of speed, risk, avoiding lock-in and accessibility. Now, these aren't deterministic. They don't fall kind of magically like manna from heaven. They're contingent on various things to do with the systems and the technologies themselves. And three really important contingencies are substitutability, system integration, and standardization. And these have all come up in different ways in Roger and Marta's talks that preceded mine. So substitutability, there needs to be a granular alternative to a lumpy incumbent, if that is what you're trying to displace. So in the case of electricity, you have modular or more granular technologies like solar and wind, which are generating kilowatt hours of electricity, as do very lumpy power plants like nuclear plants. On the system integration side, lumpy technologies often need to connect into networks or integrate into systems which themselves can be very lumpy. So if those systems can expand or accommodate more additions through marginal incremental extensions, then you have an alignment between granular infrastructure expansion and granular technology deployment. But that's not always the case. And then finally, the kinds of learning benefits that I was talking about and Marta was talking about earlier are often reliant on a relatively high level of standardization. So a kind of a collapsing of variety down onto what's called a dominant design, which allows for then this kind of replication and learning through experience. So it's a sort of 1,000 identical flowers blooming kind of scenario, this granularity argument. But to come back to the granularity advantages in terms of, if you put them all together in terms of speed, robustness to uncertainty, and also broader legitimacy, these are all critical characteristics of what we need in this rapid journey towards net zero. So what we then did in some follow-up work was apply this granularity criterion to also look at how you could evaluate funding portfolios. And this is where this work starts to become more, I think, directly relevant for the discussions around CDR. In our case, we looked at the green recovery funding, or the fiscal stimulus that was mobilized, particularly in 2020, in response to the COVID-induced economic recessions. So if you take this graphic, basically summarizes what I showed you before, that more granular technologies deliver on speed, jobs, at low risk with this distributed benefits, and these are all things that we wanted with green recovery spending. So we analysed about £73 billion, or roughly the same amount of euros, of fiscal stimulus mobilised in these 4 countries, South Korea, France, Germany, and the UK. And what we did is we looked in detail at the low-carbon technologies and low-carbon infrastructures which these countries were mobilizing public money to invest in or to target. So this plot just simply shows you our estimates of the granularity or unit cost of all these different technologies rank ordered from left to right. So some of the kind of obvious granular examples, smart meters, solar PV systems, and so forth. And then some of the obvious lumpy examples, things like nuclear power and large-scale carbon capture and storage. So a very, very wide variety on this granularity criterion. And what we then did is we looked at the spending overall, so that's shown on the x-axis, the cumulative recovery spending in each country, and then plotted that against this granularity criterion on the y-axis. So more granular is lower down, and more lumpy investments are higher up. And basically, the simple way to interpret these graphs is that the shallower the line, the more their funding portfolio was weighted towards granular low-carbon technologies. And you can see on that evidence, South Korea was, if you like, the winner in terms of its overall granularity, with a highly distributed program of investment across many different sectors. And the loser, if you like, was the UK, where you did have some granular investments on the left, but then you had a large amount of its fiscal stimulus was allocated towards a very small number of very, very lumpy investments, including in direct air capture, large-scale CCS, and blue hydrogen, or steam reformation of methane to create hydrogen with CCS, so essentially low-carbon hydrogen. So the UK really went for a kind of lumpy strategy, and other countries went for a more granular strategy. And as I mentioned before, the granularity has all these benefits for green recovery funding as well as for accelerated decarbonisation. Now, of course, there were very good reasons why countries chose to invest the money in the ways that they did. And this is a plot showing the breakdown of each country's recovery spending by sector. So the black diamond shows the total amount of recovery spending, that's up on the upper x-axis, and then the coloured bars show the share of that spending across the different sectors on the bottom axis. So 2 things to draw your attention to, actually 3 things. The first is you can see the big emphasis in Germany on transport-related low-carbon technologies and infrastructures. So this was particularly around electrification of the vehicle fleet, around scaling up electric vehicle manufacturing production lines, and also around scaling up hydrogen production, storage, and distribution infrastructure. And both of these areas are areas identified in Germany either as areas of competitive advantage in the case of the automotive industry, or areas of possible export strategy in the case of hydrogen. If you look at South Korea had a larger proportion of its green recovery funding allocated towards the energy supply. That's the yellow bar. And that's because about 2/3 of South Korean electricity grid is still fossil fuel. So there's sort of much further to go on the decarbonisation story in their electricity sector. So they align their green recovery funding accordingly. The third observation, importantly for the CDR discussion, is the very small green bars on each of those 4 country plots. And that's land use-based low carbon strategies, including all the land use-based CDR, which we've heard about earlier. And so none of the countries emphasize this in their spending, despite the relative granularity of those options. But the really key argument from this analysis essentially is that by distributing funding, this is public money, remember, by distributing it over larger numbers of smaller units, you can reap the benefits of granularity that I was talking about earlier, including this capacity to learn and improve rapidly as well as deploy more rapidly. So on these criteria, the South Korean and French portfolios performed much better. But of course, there are good reasons why countries like Germany and the UK would pursue a more lumpy strategy. The strategic objectives that I mentioned in the German case around supporting the automotive industry was one. In the UK, there's quite a big emphasis on trying to build industrial clusters around sort of former fossil fuel dominated industries and now with CCS and blue hydrogen production. And of course, there are unit scale economies that can be captured by increasing the size of a technology from small to medium up to large. And so this is all part of the logic of the lumpy investment strategy. But overall, we would argue from our earlier analysis that the more granular strategy has clear advantages. So just to then I should have said maybe at the beginning that my own research is on the energy transition and energy system change in particular. But I haven't worked specifically on CDR technologies specifically. So this is just to draw out some insights from this granularity work for the CDR discussion that we're having today. So the first is to echo the point that Roger made nicely about the need to dramatically scale up the deployment of CDR. So this is some plots from the recent State of Carbon Dioxide Removal report by a colleague of mine at Oxford, Steve Smith, and many other colleagues around the world, and Marta also mentioned this. And this is showing the scale up for direct air capture on the left, and bioenergy with carbon capture and storage on the right. So the very small square dot on the bottom left of each of those lines is the actual capacity that's been built today. And then those round dots and the line connecting them to 2030 is what's been announced by companies and other entities building these technologies. And then those grey funnels show the scale-up needed to stay in line broadly with what climate targets are suggesting. The very important thing on this plot is to note that the y-axis is a logarithmic axis. So a straight line represents very, very rapid exponential growth. And actually, you're looking at kind of 50% capacity expansions per year, which is well in excess of what we've seen in the historical record for almost any other technology over a sustained period. So what's going on then in terms of the deployment and also the innovation portfolios around CDR? Well, if you think about the CDR technologies which were being incentivized in our data sets of green recovery spending, the ones, the technological CDR options are very skewed towards that very lumpy end of the spectrum. Large-scale carbon capture and storage, large-scale direct air capture, and large-scale blue hydrogen production. Some of the land use-based CDR, which remember were very not emphasized in the recovery portfolios, are actually much more granular on this simple kind of unit cost criterion, and so therefore more likely to benefit from the granularity story that I told earlier. So that's kind of the deployment incentive story. What about the innovation story? So this is a plot showing, the top graph shows innovation activity measured by patents on the top graph over the last 20 years. And the bottom graph then breaks that down into the different carbon dioxide removal technologies. And you can see there's some spreads, and there are some land use-based and ocean-based ones in there. But really, innovation outputs have been dominated by direct air capture, that's the orange, and by bioenergy and carbon capture and storage, that's the kind of sandy color towards the bottom. Again, very lumpy technologies in this innovation portfolio. So by way of conclusion, the granularity story suggests that if you have deployment incentives, which we've seen in the green recovery funding, and you've got innovation activity, which we just saw in that last plot, that are weighted towards the more lumpy alternatives in your portfolio, you're not going to benefit as much from all the benefits of granularity that I showed you earlier. And so at the very least, you need to make sure that your deployment incentives and innovation activity are spread over that granularity continuum. The second point, and Marta hinted at this, Marta sort of said this nicely at the end of her talk when she used a sensitivity analysis of a 15% or a 10% learning rate for large-scale DAC, that it's very problematic to observe rapid learning rates in sort of modular granular technologies like solar, like wind, like batteries, and now like electrolyzers, and to apply those blindly to these very lumpy technologies like direct air capture. And actually, the historical example of flue gas desulfurization with its negative learning, this is one of the sort of historical technologies which is an analog for carbon capture and storage. And so that's a cautionary tale of overestimating learning rates in future analysis. And then final point is that system integration really matters. And actually I thought Roger's argument about the direct air capture deployment in the US, where you're co-locating direct air capture both with the renewable electricity needed to power it and with the storage infrastructure needed to do it, illustrates this point very nicely. It doesn't help if you've got very granular technologies that need integrating into new, very lumpy infrastructures, then again, you have the constraints on speed, you have the risks, and you have the limited capacity to learn that we see with lumpy technologies. And so with that, I will stop, and I welcome any questions.
Thank you, Charlie Wilson. Really, really interesting. Is the UK generally more lumpy than South Korea? And why? I mean, is that due to tradition, culture, strategic choices?
Yes, it's a good question.
Because this was related to the recovery funding, right?
Yes. So the South Korean program was exemplary in terms of its distribution of funding across a wide variety of sectors, a wide variety of beneficiaries, and a wide variety of granular technologies, both in buildings like insulation, in the energy supply like PV, in the mobility sector like electric vehicle adoption incentives, charging infrastructure, and so on. That was very closely aligned with South Korea's net zero strategy, which was also interlinked with its digital strategy. And so a hallmark of digital or kind of more smart technologies is also that they tend to be relatively granular. In the UK's case, they did have some granular spending programs in their portfolio, particularly for building energy efficiency retrofits. But the big one, which was a £2 billion program for energy efficiency, was actually cancelled halfway through due to delivery failures, due to delivery failures. But the UK does have an emphasis on these very lumpy replacements for old fossil infrastructure, particularly in some parts of the country, like in South Wales and North East England. And so that led it, I think, from an industrial strategy point of view, to focus on these big lumpy investments.
Okay, really interesting. So we have a few questions coming from the audience. To apply granular CO2 capture, you also need a granular source of CO2. How to address this? Is that plants or what do you suggest?
So I'm not 100% sure I understand the question, but I'm not sure if it's to do with the concentration of CO2 in ambient air, which direct air capture is going for, or whether it's to do with the much more concentrated CO2 that you get in smokestacks in thermal power plants, if that's what the gist of the question is, or whether
Well, we don't know. So you can answer whatever you like.
Well, okay. So I'm going to interpret the question in the other way, which is about the granularity of the capture unit. So simplistically, are we thinking about very small scale capture units like an individual tree, or are we thinking about very large scale capture units like a CCS unit put on a big thermal power plant, or a dedicated direct air capture facility? And so this is where it gets obviously quite hard to make a direct analogy between trees and hardware. So all the historical analysis we showed was on energy system technologies. And so I feel cautious about overly applying them directly to all the land use-based CDR options. But in principle, the granularity argument still applies in terms of the unit size of discrete investments needed to capture and store carbon from land use, as it does in the energy system. So I still think there's an applicability. And so the granularity arguments that I made with respect to energy, I think apply more broadly to CDR portfolios.
Mm-hmm. Okay, a question related to one of the graphs. Some of those R2 values on granular tech looks low. What's going on with all the outliers?
Yes, okay, that's a great question. So the R-squared values is a measure of the goodness of fit of those trend lines that I showed you through all the data points. And the higher the R-squared value, the better the fit. So the first thing to say is that when you're trying to explain any given outcome, like the learning rate, like the deployment speed, or like the number of jobs, and you're trying to explain that as a function of one single technology characteristic, its granularity, you would expect that to be a fairly crude relationship. So to some extent, the fact you find any positive trend is a significant finding in and of itself. There are lots and lots of other reasons which will shape whether it's employment, deployment speeds, or learning, not just unit scale. So variation is really important. The outliers, in each of those graphs, there were some outliers, and this is discussed at length actually in the paper. So whoever asked that question, I would point you towards the original paper that I was speaking from, where we discuss exactly why some of those outliers are so interesting. So as one example would be, there are examples of very rapid deployment speeds from certain technologies in and around World War II, where there was a kind of a concentrated mobilization of policy efforts, of finance, and of technology innovation in order to get technologies to market rapidly in the context of wartime mobilization. And so those were outliers, if you like, for very good but anomalous reasons.
Okay, Charlie, a final one, a tricky one. Is ChatGPT lumpy or granular?
So I'm sorry, I'm laughing because I haven't actually thought about that specific one. Digitalization tends to have very granular characteristics. For example, in how it can be, very rapid innovation cycles, very rapid experimentation, relatively low unit cost replacements, and so forth and so forth. However, in the particular case of ChatGPT, although the interface with any given user is obviously highly granular, it's trained on an extremely lumpy data set of all the stuff that it's hoovering up in order to improve its algorithms. So maybe I can hedge my bets on that question by saying it's a granular application that sits on a very lumpy infrastructure.
Okay, so that's both. Charlie Whitson, great pleasure to have you here. Thank you very much for joining us. And thank you, ladies and gentlemen, for all the excellent questions. Just keep them coming, because now we're moving to a panel debate. We do actually have a microphone in the room as well. So when we take questions at the end of the panel debate, you can use the microphone as well, if you like. So let's invite our panelists on stage. You've already met Martha Victoria and Roger Ains. So they are the first two participants. Then secondly, we have Anders Hoffmann, Deputy Permanent Secretary, Minister of Climate, Energy and Utilities, and also Governing Board Chair at IEA. And then Jan Hugfeldt is joining us, Chief Commercial Officer with the Climeworks. Climeworks is a private enterprise working with carbon dioxide removal via direct air capture. And he's probably going to tell us more about that, but he's coming from the technological side of things. So thanks very much for joining Jan, Anders, Roger, and Martha. So what we're discussing here is some of the things we've touched on already. The granular versus lumpy issue is, I think, also really interesting, but the taking off point, Martha, is your presentation. How do we learn fast and efficient? Because speed is an issue that all the speakers has been touching on so far. Anders, you've been here all day, so maybe you can maybe just a quick reflection on some of the things we've learned during the first 2-3 keynotes.
That was a very sort of head-on. I think I learned that I'm chair of an institution that really can't get anything right on the data. No, sorry. No, I think there's two things that struck me. I mean, first of all, maybe just my background, even though I work in the ministry now, is I'm an economist. So I think in many ways I would have used different words to coming to some of the same conclusions. Because I think a lot of this about systems, I think there would be much more about, okay, how do we set the incentives right to have this massive scale of solar? I mean, it was a feed-in tariff in Germany that created a market. You had 15 years of bankable German guarantee. You saw large capital fund moving in. So I think there's a lot of sort of insights, but very different language. I think that was the first try. And the second one, when I think many of these things tend to be more complicated depending on technology. I think many of the technologies that we'll probably be talking about later really need to have this integration into the system. I think that was also the last conclusion on the slide. I mean, how do you put that into a lumpy system? And I think from my perspective, I think that probably one of the biggest challenges moving forward, that all of these technologies are based on value chain, and most of these value chains do not exist at the moment. So you need to scale something up where you have a chicken and an egg lying around and try to sort of get them to coordinate. I think those were sort of the two things I was scribbling notes about.
Yeah, really interesting. And clearly, I mean, these value chains are very much the responsibility also of the Danish government or the US government. And as you say, we don't have them in place at the moment, so that's another challenge ahead of us. Jan, what did you pick up from this morning?
Yeah, thank you for having me. Well, first of all, I picked up a lot of hope from Marta, a lot of very interesting new data from Roger on the US, and inevitably we would love to have that data also outside of the US. But coming back to the hope. I mean, in Climeworks, we obviously live this on a daily basis. How do we scale as fast as possible the direct air capture technology which we have? And you've heard it from Marta, but also from Charlie. There's an installed capacity today available of about 10,000 tons, right? And today we have a running facility in Iceland for the past 2.5 years where we are learning a lot. And here we're talking a few thousand tons. And the next biggest, which is actually 10 times larger, is going to go online in January. And much of that learning is baked into the next. And then just to give the full picture, we also applied for funding from the DOE. We were selected for 3 sites for further funding negotiation. And there, specifically in Louisiana, you've seen it on Roger's chart in the south of the US, we are looking at scaling towards megaton by 2030. So that's really on our roadmap, and it has to be said, it's a massive challenge on a number of ways. And maybe to quickly conclude what actually really would speed up learning. And for us, it is really deploy. Because when you do things in the lab, that's one thing. You can get the thermodynamics right and the kinetics, and you have a good understanding of the chemistry. But translating this into real life direct air capture is a massive undertaking, and you actually start to learn a lot of things which you didn't even expect you would find in first place. And what Climeworks maybe sets apart from many others is that Climeworks, existing for the past 15 years, have been going from lab to small pilot to larger pilot to first of a kind industrial scale, which we have now operating in Iceland, and we will continue that journey. And that is really necessary, we believe, to make sure that we de-risk of what we are doing, rather than going from lab to megaton.
Yeah.
Right?
Okay, just let me know whenever you have anything for the debate, and I'll let you in. But Roger, maybe also a few reflections on Marta's presentation this morning. What do you think there is to learn from solar PV and the development there for other technologies? Because that's the topic of this debate.
Yeah, this learning rates have been a kind of an arcane topic in engineering schools that have now become very pertinent. And for us, we like to find examples that look just like the thing that we're trying to scale. And unfortunately, PV is not like anything else because it is so granular, which is marvelous. It's been wonderfully beneficial. But what we find is you have to separate the capital activity from the operating costs. Operating costs don't tend to be subject to much learning. Capital is where all the learning tends to occur. So, the smaller things. And then, the second challenge there is the amount of carbon benefit you get from doing it. So as I showed you with soils, the carbon benefit it's easy to get, but it's relatively small. So this is another trade-off you have to consider in terms of policy decisions. And one of the reasons that the United States is investing heavily in these large-scale things because that's where the large benefit comes, and it's slow to get.
Yeah, Martha. Clearly which I think Jan will allude to in a second, molecules are very different from solar. But what do you think from your presentation could be interesting anyhow to some of the other technologies?
I fully agree on that comment. I didn't use the learning rate for solar as saying we can obtain that for DAC because I don't think that's possible at all. So it's an open question. What could be a learning rate that we can attain for a technology like capture? But I think there are elements in the fast cost reduction of solar that are needed for the technologies to learn. No? So besides the trying to find technologies that are closer to the granular description, we have the need. We call it learning by doing. So we have the need for doing to capture the learning. And I think this is similar to what Jan was saying. No? We need policies that create a market, or we need to go out of the lab, build the technologies, and learn and capture those learning. This idea of let's wait until we need the technologies in 2050, that's for sure, from my point of view, not gonna work. So the big message, or one of the things that I learned from the solar is we need to go through the period where the technology is too expensive, and we need to support that technology.
But what have you learned from policies and stimulation during that journey that PV has been through?
Yeah. So one thing very characteristic of PV is that you need to make an investment, and most of the expenses are capital cost. So you make the investment on day one, and then you expect to capture the revenues to, for instance, save money in your electricity bill for the next 25 years. So that means you need to have some security because you are making a big investment on day one. And there are the regulatory frameworks, the government, in general, the framework around the technologies which can give the security so that investing in new technologies is seen as a good option. Mm-hmm. So instead of just saying, we don't know what's going to happen, everyone can try, I think government or regulatory frameworks can provide security, and that's also what it's needed for technologies that are very capital intensive. Mm-hmm. And most of the technologies needed for the transition or for the capture are these kind of capital intensive technologies.
Yeah. Roger, Anders, any reflections on these examples coming from Martha? Roger, what I didn't mention was that you're also an advisor to the US government. You're here as a private person or a scientist, but you're well aware of the US stance to innovation and development of green technologies. And Anders, you're here as a representative of the Danish government. So. Reflections on the stimulus that Martha spoke about, Anders?
Yeah, maybe, but just as a civil servant, not the government.
Excuse me. Yeah, well, you're not a politician.
Good.
I know that.
No. Okay, I think I completely agree about this point about creating the market, which also was made by Jan. That you need to have a market in order to be able to scale up these things. So completely agreeing on that. I think what is very many times difficult in that is that I think there's two things you also need on that. You also need to, in order to create that market, you need to prove whatever you're doing is working. And that's quite easy if you produce electricity. But some of these bio capture, we will put something in the ground and it will stay there for how many? Sort of the technology to actually come up with a number and say, okay, that's 1 million tons of CO2 forever or something. So, and sometimes we tend to forget that in the research. So when we look at different technology, what's to to subsidize. I mean, we're really keen on biochar in Denmark, but we still haven't had sort of the proof that you can put that in the ICCP report and send it. So I think this.
No, but because it takes 50 years.
Yeah. So there are still some challenges. I mean, how can you prove a technology works good enough for somebody to want to pay for them? And then I think my final point is, I think one of the things that hopefully we're doing great in Denmark, or at least trying to do great, is really to have an interaction between the public sector and the private sector in the scaling phase. Because, I mean, how we can do tons of work, but we will never know all the barriers you will hit as you're scaling up technologies. So you need to have sort of a very close link between companies coming back and say, hey, we can't do this because of that, and then somebody will have the will to change that. I think those would be sort of the key component in my scale fast roadmap.
Yeah. Roger?
One of the things that we're doing in the Department of Energy over the next year is buying a lot of removal. We're going to spend $35 million buying removals. We would like to have 20 companies that we buy it from. What are we after there? Well, certainly we'd like to remove some CO2 from the air, but mostly we're trying to learn how that's done. What matters? How do we do the measurement? How can private companies learn along with us so they can see that? But this is another one of those processes that you have to do in order to see how it works. Just developing the technology is one thing. You have to sell it. Well, we're offering to buy it so we can learn more about that.
What would you say is the most important difference in the US stance towards the EU stance?
So, private citizen standing here.
Of course.
The United States has decided to go entirely with carrots, and the EU is almost entirely sticks. And we tried other things in the United States for a very long time, and I'm very excited about the carrots because it puts the money into the hands of the innovators, as opposed for whom this is their entire business, as opposed to having a small hit on the profitability of a very large company that would really like to just ignore it, or basically it's not as big an influence on them. So the money is better leveraged. And we're already seeing this. We're seeing enormous investment and enormous activity in the United States because you're directly putting the money into the hands of the innovators. I'm quite certain that over time, those policies will come together. We will need to regulate in the United States, and you will need to incentivize more in the EU. And we're going to learn from each other right now, and that's kind of exciting.
Yeah. Jan, seen from the industry perspective, which stance is the most interesting to you?
Well, I mean, I can only applaud the US for what they've done, and you actually can, and whether this is correlated or not, I believe it is. You announced the Inflation Reduction Act. It started to roll. You also announced the first purchasing program. I hope that this is going to grow. I know it will, but obviously, hopefully sooner than later. But what is interesting is that coincidental, you actually have big corporations starting to make significant investments. And there is 3.5 billion, but there is much, much more which is going to follow those 3.5 billion to actually create a really sticky carrot. Now, I believe we also need to have the stick. And why I think the stick is needed, and ultimately I think maybe the European and the US way of doing it will converge, because we need to also set standards. It's, CDR or carbon dioxide removal is not equal carbon dioxide removal. Trees might be maybe more granular than direct air capture, but trees alone won't make it. And trees would have to be repeated over and over again. You said that, Roger, to actually have any kind of permanence, and there are many more risks with it. So if we are burning fossil fuels, which actually ultimately got there over millions of years, we might not be able to just replace them by trees, which maybe have a lifetime of 200 years. We need to have permanent, durable removal as part of the portfolio. So we call it like for like. Like if you are burning a lot of fossil fuels, you also need to look at replacing those through durable solutions. And that requires more of a standard setting, more of the stick, I think, than the carrot. And then it needs to be legitimized, and policy can actually help on that too, right? That the social aspect, I think we will come to it later today, is a really, really important one, because communities, they don't like to have any of these installations in their backyard, right? And so that actually requires a lot of muscle building and work, which is typically underestimated, especially in the early stages.
Yeah. Any reflections to Jan's thoughts?
Maybe could I try
Go ahead.
with a bit of on the differences between the US and Europe. I think one of the things that we've tried to do in Denmark is I completely agree. If you sort of have the small sticks, I mean, you don't get giant innovation, but I mean, you get very good energy efficiency. You get a lot of sort of small improvements. You get a lot of all the things you've seen in Denmark. So I think so far the Danish strategy has been sort of have some sticks, and some of them are actually quite big. But combine that, for instance, with sort of a special subsidy scheme on green hydrogen, a special subsidy scheme on CCS. So really take some of the technologies where we know that the jump is quite high, and really say, okay, then we have the subsidy on those, and then we'll have the sticks, and sort of try to combine those two. So really have subsidies for the big innovations, and then the stick to sort of make sure that people actually jump.
Yeah. Martha, does this make sense to you?
It makes a lot of sense. Yeah, I was also thinking on bringing this idea that we are developing the CO2 capture and conversion technology while we are changing the other part of our energy system or system in general, no? So because we can see that it's challenging to get to these amounts of CO2 capture, all what we can manage to do with mitigation, all the CO2 emissions that we can avoid, will also make the challenge a little bit less traumatic, no? So it's also important to discuss when do we do things, and I think now we need to massively invest in wind and solar, decarbonize all what we can, and in parallel develop the capture technologies. And if I can say one thing else, I thought it was interesting to learn from Charlie that the outliers in terms of the speed of some technologies can be explained by the fact that during the Second World War we made a huge effort. I would say, as a citizens, we should be making a similar, if not a larger effort to mitigate climate change. We are rich societies, we should be able to make transition fast, not only because we are on a war, no? But because we try to make a more livable world. So, in my view, there are historical speeds or historical learnings, but if we think big, we can also go faster.
Yeah. Okay. Jan, when we spoke earlier, we discussed how to scale, and you had a few reflections about cost. You said cost cannot be understood in a lab experiment. So how do we enable scale? Running a manufacturing line, you said, is just very different from a lab experiment. So can you elaborate a bit on how we're sort of moving from the lab to the manufacturing line? Because it's only when it's in the manufacturing line that we understand, as you said, the magnitude of the task.
Yeah, just to illustrate this in a very simple way. No matter what you produce, whether this is mobile phones or Pampers, diapers, your manufacturing line, one of the ways of characterizing is you look at the overall equipment effectiveness of your line, and that is a product out of the availability. So how much of the time the line is standing versus running, the performance, which is ultimately the speed, and the output. Do you actually get good quality output, or do you have faulty products at the end? And when you run a first of a kind installation like we do in Iceland now for 2.5 years, you fight for these three factors. And say you get to 80% in availability. That means 20% of the time this plant is not running, 80% of the time, 365, 24 hours, the plant is running. In speed, you actually get to 80%, right? and the output, you also get to 80%. Well, what does it give you? 50% overall, right? It's a very simple, you do well, figuratively speaking, in running a first plant, and yet you are just at 50% overall equipment effectiveness, which have massive impact on your cost. So that, in addition to the entire scaling of your supply chain, all of these factors drive first your costs up. There's a cost curve going up, and you realize, we didn't think of that. Before you actually then, through massive scaling, you actually drive costs down again.
Interesting. So let's have a few questions from the audience before going for another cup of coffee. And there's $1 million question from the audience, which is really good. How to identify the most promising and scalable technologies for carbon capture? Who would have a go at that? Yeah, Roger.
I'll have a go. The first thing about carbon capture is you need to look at things that can't be done better by another method. If you can replace it, doing a large coal-fired power plant, CCS, it's simply cheaper to use renewables. So that's the first criteria you put. But I think the scale factor that Charlie talked about is really important. We can't go after these gigantic facilities first because we won't learn. We need to choose to go fast and choose to do the small things. Here in Denmark, a really important thing is biogas. Half of the carbon that comes out of a biogas facility is carbon dioxide. We should be capturing that, putting it underground in the new facilities that you're building here. Things like that can really help.
Honest?
I think the simple answer would be, put a price and have a competition. That's
simple question, simple answers. Okay, another question. Do we have enough CO2 storage capacity globally for the estimated 730 gigatons of stored CO2 by IPCC? Anders, the Danish government is very much into CCS as well.
Yes, I think we have plenty, not for the whole world, but at least for the northern part of Europe and Denmark. I think that, and we're very keen. Actually, that's actually also part of the sort of the learning and the scaling. The reason why we're so keen on having foreign countries to store CO2 in Denmark is simply to get the cost down, also for Denmark, because we know there's going to be learning, there's going to be economics of scale. So having some German CO2 coming up will actually reduce the cost for Danes.
Okay, Jan, there's a question for you here. What is the best way to finance a first-of-a-kind plant? It's probably not bankable yet.
Yeah, that's a core question, obviously, to our day-to-day life. So the first plant is partially funded through equity and partially through project financing. And as we go along, once you get towards megaton, we are talking actually billions of dollars which are needed for those infrastructures. And inevitably, this is not financeable through equity, only a small part. And to actually make those investments, that's ultimately my task as Chief Commercial Officer. I need to find customers for the future lifetime capacities of these installations. And that's also where, and coming back to what Marta said initially in her keynote, it is really important to drive early demand. Because if we don't act now and are pragmatic about it and are doing our reductions, but also starting to actually purchase removal, we will also not be able to actually scale this from the 1,000 times scaling to megaton to 1,000 times scaling to gigaton, right? And if you just a fact on this, there are about 4.5 megatons of CDR purchased to date. Microsoft purchased more than 3 of those 4.5. So it is really Microsoft which drove much of this. And in the beginning, they have a formidable, huge team, really experts in what they're doing, both on the project financing as well as on the carbon decarbonization. When they started, they started in a very pragmatic way, and they made their bets to make sure that early technologies actually can get a lift off. And this is so fundamental, it is catalytic. There are over 6,000 companies who made a SBTI, a commitment to net zero, according to the rules which exist today, and only about 30 have purchased so far. And this is growing massively. If you look at BCG's last report, you will see that the actual demand by 2030 is way outstripping supply. And so that's an alarming picture. So the appeal to everybody who is sitting in corporations is to actually say, look, I mean, yes, analyze, and we need to continue analyzing and looking into where can we optimize, but you need to take a pragmatic approach and make first commitments, because even many small commitments are making a big dent for companies like Climeworks.
Okay, really interesting. Lots of good questions left, but we have a coffee break coming up as well. So Martha, Roger, Anders, Jan, thank you very much for joining.
Thank you again.
Good. So a coffee break is coming up, 15 minutes. If you need a toilet, the toilets are in the end of this room. Anna Leyborn is still with us, so she's joining you in the library and continuing to draw the conference. Enjoy. Ladies and gentlemen, welcome back. Welcome back to the final part of Carbon Forum 2023. We do still have Anna Leyborn with us, the graphic facilitator, and she's just about to get a microphone on, and then I'd like to hear Anna, what she experienced so far, and what your participants have discussed with her so far. Come, Anna, and join us. You made a few drawings here. What did you discuss with the participants?
So the main takeaways so far are that this issue, you look at many solutions and the problem as a global problem on a bigger scale and not focusing on just one solution. And this is somewhat similar. It is a modular. You should take a modular approach and look at the many solutions together to accelerate, because very often we've been looking at one technology and see, can this accelerate and do the scaling? But actually, you can scale from putting different technologies together, and it's super important that these solutions learn from each other.
Yeah.
Then we have. I've had a discussion with a participant about money is fiction. What is important here is resources, and what does it take in resources to do these things. Let's not talk about the money, but let's talk about the resources, because they are real. Then who should take the decisions? That was also a discussion I had. Should it be authorities, scientists, industries, citizens? And probably it should be all together, but how do we do that? And then from community level, that was from Roger Ains's talk about the community level was important too. That was a main takeaway for but the learning and communication with scientists. Then we have two last ones. One is everything is non-linear, and that is good, because everything you put in aren't linear either. And then we have the chicken and the egg arriving at the same time, and this is a scenario that we would really love to have.
Yeah, that's always the big issue for the scientists. Did you get a chance to discuss what people expect from the rest of the conference? I mean, because this is relevant to what we are going to discuss in the concluding debate, societal acceptance. Did you get the chance to talk to anyone about that?
No, I think people are really thinking a lot of knowledge so far and a lot of discussion so far. So we were mostly talking about what has happened so far, but they're eager to hear about the next things that are going on.
Exactly. And as I said in the beginning, you are going to live draw from that debate, which I am looking forward to. That's pretty exciting. Yeah, and then we'll have a quick recap after the concluding panel debate. So thanks a lot for now, Anna.
Thank you. And the live recording will be up here.
Yeah, exactly.
It will be so small that you probably can't see it, but in the wrap-up, I will zoom in so that you can see it, and it'll be sent out afterwards.
Yeah, we should all be able to follow it live, so that's really extraordinary as well. If you want to admire some of Anna's work, the first one is over here, and this one is probably going to end up the same place, so you can see it when we're done. Thanks for now, Anna.
Thank you.
So in this part of the conference, we have another 3 presentations and then the concluding debate. And our first speaker on the stage is also joining us from quite afar. Harry Atwater is a professor of applied physics and material science at the University Institute of Technology, also known as Caltech, and he's also a CORC PI. And he will speak about ocean CO2 capture and the journey of Captura. The microphone is yours, Harry.
Okay, thank you. Yeah, I'd like to tell you a story today that builds upon some of the themes that we've already heard about speed and scale and cycles of learning. This is a story about a concept and, in fact, a company that are about just a little over 2 years old, 2 years and 2 months old. Focused on direct ocean capture of carbon dioxide, a new approach for carbon dioxide removal. And as we know, the Earth is remarkably resilient, and our Earth consists of a variety of ecosystems that are working to absorb carbon dioxide from the atmosphere and to emit carbon dioxide back into the atmosphere. But the problem is we have an imbalance. We have an imbalance that's coming from our fossil fuel emissions, and that imbalance is leading to rise of CO2 in the atmosphere, the famous Keeling curve that is this sobering reminder of our trajectory for carbon accumulation in the atmosphere. But that is balanced by the resilience of the world's ecosystems, and in particular, about 1/3 of the carbon that we emit into the atmosphere from our human industry and anthropogenic sources ends up in the ocean. And so there's also this green curve is a Keeling curve for the rise in dissolved inorganic carbon in the ocean. And the blue curve here is in fact a Keeling curve for the ocean pH. The ocean is acidifying in response to the accumulation of absorbed CO2 from the atmosphere. So there are many ways to perform carbon capture using the ocean. There are both biotic and abiotic approaches. So I won't spend detail telling you about all of them. There are a variety of approaches that involve basically collecting using photosynthetic apparatus in the phytogenic layer of the shallow ocean to capture carbon and then to move it to the ocean floor, to use ocean alkalinity enhancement, for example, to revive and restore coastal estuaries as sources of blue carbon removal. What I'll focus on today is this process called direct ocean capture, which involves direct removal of CO2 from seawater. I'll just point to some useful references here and note that many of these are summarized in the Carbon 180 report. So the way direct ocean capture works at a very, very simple and high-level view is to remove seawater from the ocean, from the shallow ocean, which contains this dissolved inorganic carbon that is in excess of what it was before the onset of industrial civilization due to carbon emissions absorbed from the atmosphere. And to use a electrochemical process to remove CO2 and store it in geologic reservoirs, and then to discharge that seawater back into the ocean simply without its carbon. And in doing so, that will cause a modest rise in the pH of the ocean. We're essentially undoing ocean acidification that has occurred as a result of carbon emissions into the atmosphere. And so when we undo ocean acidification in the shallow ocean layer, this is now reversing this is now accelerating the process of carbon drawdown. You could think about this as the inverse of the situation if you open a can of Perrier water and you have a drink of Perrier water, and suppose you left it overnight on your kitchen table. The Perrier water would go flat. It would be bubbly when you first open it, and then it would go flat. And that's because there was the carbon concentration in the water is out of equilibrium with the atmosphere. And similarly, we can reverse that process by decarbonizing the shallow ocean layer and using thermodynamics and kinetics to draw down CO2 from the atmosphere. So you can think about this as not direct air capture, but indirect air capture, using the ocean as the world's largest direct air contactor. So this is what it looks like at a somewhat more detailed view, where water is withdrawn from the ocean. A small amount of it is used to drive the electrochemical process, and this process uses a pH swing. It causes acidification of the water that's pumped from the ocean. That acidification, as I'll show you in a moment, is the key to removing CO2 as a gas from the water. Then the acidified ocean stream is combined with the complementary base that's generated so that we create, through acid-base neutralization, simply the same seawater that we had to begin with, except with the CO2 stripped from the water. And this is described in some more details. For example, in the Captura carbon dioxide removal pathway, you can find, if you go to the Captura website, you can find this. It's a document that gives a roadmap for how this process works and how it is consistent with ocean safety, which is a very important consideration that many questions that are being addressed at the moment. And very importantly, also something called MRV. It's an important acronym that everybody in this room needs to know, which is monitoring, reporting, and verification. Carbon credits are only environmentally or economically useful to the extent that we can quantify how much carbon has been removed in the process and its permanency of storage. Both of those things are key to determining the ultimate drawdown potential for a given CDR method. So now we're going to do a little bit of chemistry. I'm a scientist, I'm a professor in addition to being an entrepreneur, so I have to do some chemistry here for you. And so basically, carbon dioxide comes into the ocean first as carbonic acid. CO2 goes in as a gas and it forms carbonic acid. That's the fizzy water in Perrier, in your Perrier water. But then quickly, in order to equilibrate at the native equilibrium of the ocean, at the pH of the ocean, 8.1, it dissociates to form bicarbonate. And the bicarbonate, if you remember your chemistry from high school, has a -1 charge, and so that it dissociates a proton, and that proton is the source of the ocean acidification. That's why the ocean is acidifying. So an interesting feature about ocean is that carbon in dissolved inorganic carbon is concentrated on a volumetric basis 120 times more densely than carbon dioxide in the air. So this is quite an interesting feature that makes essentially a more efficient concentration from the point of view of pumped fluid. So this is a plot known as the Bejerum plot of the equilibrium concentrations of CO2 in the ocean. And you can see here as a function of pH. And at the native pH of the ocean, the equilibrium concentration is dominated by bicarbonate. If we now were to have a process that could make the ocean water that's withdrawn be more acidic, it would then be dominated by CO2. So we can use this principle that governs the removal of fizz from an open can of fizzy water, called Le Chatelier's principle. If we add acid, we now drive this towards gaseous CO2. And so then that drives it towards CO2, where we can strip out the CO2. And if we now move it back the other direction, we can bring the pH back, restore the pH back to a pH slightly higher than it was to begin with. That tells you about the thermodynamics. The kinetics of which is the rate at which things happen around the world, is determined by the mixing at the ocean-air interface. That, of course, is driven by wind and waves. In the calm areas of the ocean, the mixing times are a little bit longer, and in temperate to northerly ocean zones, where there is more wind and wave. Typically, there's more mixing. And this map shows the time scale is typically on the range of a few weeks to a few months for that equilibrium to occur between the shallow ocean and the air. So now let's take a little bit more modular view of this decarbonization, and note that we're basically taking ocean water, acidifying it. Acidifying it allows us to strip out the CO2 gas, so we do gas extraction, and then we basify and then discharge water back into the ocean. So every chemist will recognize that all we're doing is balancing mass and charge, and even if you don't, if you're not readily following all these equations, it's important for me to show you the equations, not for you to understand all of the equations, but to understand that it's possible to quantify quite precisely exactly what is the mass balance and what is the charge balance. So those equations can be represented on a very interesting nomogram, and that, by the way, this nomogram is contained in the document that I mentioned earlier, the Ocean Pathways document. Acidifying seawater brings now from the pH of the ocean. We can now bring down the equilibrium so we bring down acidification, we bring down the pH, and now we reach a situation where the orange lines denote the partial pressure of CO2, which is in equilibrium, and then that gives us, that means that the partial pressure of CO2 is way in excess of 1 atmosphere. So we can now, the CO2 can be readily extracted through a gas-liquid contactor. Adding the base now brings the pH back up again. And in this case, now the partial pressure of CO2 that's in equilibrium is much less than the amount that's in the atmosphere. And that's the thermodynamic driving force that drives the drawdown. So it's the capacity to do this involves tracing around this cycle: drawdown, acidification, CO2 extraction, basification, and so forth. So just to summarize, this is a process that involves two feedstocks: ocean water, renewable electricity. That's all. There is no other input to this process. There are only two byproducts: decarbonized ocean water and a relatively pure CO2 gas stream. So there's a little bit of air and a little bit of water vapor in this gas stream. So there are no materials criticality issues. There are no precious metals used. In fact, not much metal at all. Most of the materials that are used in our process of basification and acidification are membranes. In fact, the membranes resemble those that are used in fuel cells or electrolyzers. The energy provided by solar energy. So I was very intrigued by Charlie Wilson's analysis about modularity. You can think of this as a process that fundamentally has to scale, but the components are very modular. You can think of this as basically electrolyzers or very similar electrochemical functional units. Precisely, they're electrodialyzers and solar panels. And the energy, operating expense is dominated by the energy use. So it's a very interesting case where the total costs are dominated by energy rather than by capital and materials. Furthermore, the fact that we form acid and base is a very interesting form of energy storage. It's essentially a battery. The significance of this is that solar and wind are variable sources of electricity generation. They are intermittent. Solar is predictably intermittent. It doesn't produce in the nighttime and produces in the daytime. As a result, the electricity cost varies throughout the day unless you have storage. And so we can generate, for example, electricity or we can use electricity generated at peak electricity generation times when electricity is cheap, $10 a megawatt hour, to make acid and base that's used for the rest of the diurnal cycle. So essentially it allows you to take advantage of time of day electricity pricing. and it doesn't require instantaneous energy use. So it's very, very well matched to intermittent renewable sources of electricity. So water is then discharged from a plant here, and it's slightly elevating the pH of the ocean. This is what you can see in a multi-physics model that shows this plume of decarbonized ocean water coming out. We've also done measurements here. These are measurements done on the ocean, looking at the rise in pH as we bring in decarbonized ocean water into native ocean water, and the pH rises here from about 8.1 to about 8.35 or so within this small tank. And as the plume of ocean water disperses out, this pH rise becomes even more modest. Importantly, as it spreads out across the ocean, it's now acting like a direct air contactor, a large direct air contactor, eventually spreading out over many kilometers. So we began this journey on a benchtop in a lab at Caltech in 2020, in February of 2020, and built a unit that's not much bigger than the size of the top of this table right here. This unit was able to show a record low energy consumption of little less than 1 kilowatt hour per kilogram of CO2 at the lab scale, and already demonstrated CO2 capture at about 80% efficiency. So what's interesting about this technology is actually the efficiency at a small scale is exactly the same as the efficiency at a large scale. That's characteristic of electrochemical technologies. So there's no inherent reason for scaling other than finding the right balance between OpEx and CapEx. So the engine of this is effectively what's called a bipolar membrane. So these are membranes that selectively allow transport of protons or anions. And so this is a bipolar membrane is a laminate of two membranes. And what it does, if you apply an electric field across the membrane, is pull apart a water molecule. It pulls apart a water molecule into a proton and an OH minus. And in so doing, it creates an acidic volume of water and a basic volume of water in an electrochemical cell that looks like this. And so this is very much like the design of a fuel cell or an electrolyzer. It performs a process called electrodialysis rather than electrolysis, which actually is more energy efficient than electrolysis. If we go down to the molecular and nanoscale, at the interface between these two membranes is a catalyst. This catalyst is a form of carbon called graphene oxide, and it facilitates the more rapid dissociation of the water. So this is just to show you that all of the components of this are basically polymer membranes and something that's akin to carbon black, very inexpensive materials. And so one of the things that's interesting is that this is allowed then at very high current densities, an amp per square centimeter, record low energy usage, record low voltage. Voltage times current is power, and power times time is energy. So this is compared to the commercial competitors, the high current density performance. So this is a dramatic improvement, and one of the reasons why this is an approach that looks attractive for direct ocean capture. So I'm going to now tell you a story about the scaling, the speed and scale. We began in 2022, last year, by deploying a system that captures 1 ton of CO2 per year. This year, we began and commissioned at the Port of Los Angeles a prototype that generates or captures 100 tons of CO2. So these represent pilots that allow us to achieve cycles of learning, but also increase the scale. This pilot is going to be, and something identical to it will be deployed with our partners Deep Sky in Quebec, harvesting the resource of abundant hydropower electricity in Quebec in mid-2024. And we're also working with our partner Equinor to build a 1,000-ton pilot plant on the Karsto site in 2024 to produce carbon captured from the ocean in Norway. So this is what the 1-ton plant looks like. It's about the size of a refrigerator, or maybe a refrigerator with a freezer sitting on the side. You can see here driven by solar panels at Caltech's Kirchhoff Marine Lab in Newport Beach, California. We've operated this system for more than 3,000 hours, gaining a lot of data that looks like this, where the carbon removed is at about 90% efficiency, and it's a relatively pure stream of CO2. This is the 100-ton facility, looking what it looks like in the lab, and was commissioned in 2022. In 2023, it moved to the Port of Los Angeles on this barge here. You can see all of the systems here conceptually are exactly the same as they are at the 1-ton level. Things are getting a little bit bigger for the storage tanks for electrolytes, but everything else is pretty much the same. So this is the pathway that we see going from 1 ton to 100 to 1 kiloton to 10 kilotons to 100 kilotons, eventually to megaton scale plants. So it's a technology that we believe is scalable and a very simple one where it is driven by renewable electricity and produces only decarbonized ocean water. So from the science viewpoint, we've made a process that allows us to use electricity in a very energy and efficient manner to promote pH swing for stripping CO2 from seawater. We have pilots at increasingly larger scales of development. And very importantly, we're working together to further develop monitoring, reporting, and verification, as I just reported, and to explore environmental co-benefits. For example, working together with partners that allow us to determine the extent to which slightly elevated pH can restore the ocean health of coastal estuaries and be, in fact, beneficial for cultivation of aquaculture cultivation, mussels and oysters and so forth. And finally, a vision for where carbon capture from direct ocean capture and Captura can go in the future. Thanks very much.
Thank you, Harry. I know this may not be at the core of your research, being a physicist, but can you tell us a bit about what the consequences are for biodiversity in seawater, that we have a large amount of CO2 in seawater? So, marine biodiversity, how's it being affected?
Well, that's very important. And as you know, the acidification of the ocean has had a negative effect on biodiversity. It's causing, for example, the bleaching of coral reefs and the damage to coral reefs worldwide. In coastal regions where freshwater discharge reduces the pH, that also reduces the growth rate of larvae and aquaculture and so forth. So we think that there's some very interesting potential co-benefits to being able to control and modulate the pH in these regions, and in fact to restore the ocean to its original pH. Now I should mention that fully restoring the global ocean's pH is only going to come about when we remove all of the excess inorganic carbon. So this is, of course, a global...
it's a monstrous task.
Yes,
yes. Yeah, I can tell. Okay, question coming from the audience. How does DOC compare to DAC in terms of energy input and costs?
Okay, that's interesting. So I think ultimately to do this in a quantitative basis, I invite you to invest in the company, whereupon you can go into the data room and see all the detailed techno-economic analyses and so forth. But at a very high level, one of the reasons that Captura is the costs are comparably lower than benchmark DAC systems is that the air capture unit is essentially the ocean. So there's no capital expended on the direct air capture. All of the capital goes into the CO2 removal. And in fact, the entire process, as I indicated, is dominated by energy costs. So in fact, that's why we've been keenly focusing on ways to use the variable pricing of electricity to our advantage.
Yeah. Okay, so we have a question about scale, and that's going to be the final one for you. What is needed, or what is it possible to reach megaton or gigaton scale for your technology?
We believe that that's possible. And then I think the very interesting question in the minds of everyone listening here today is, what will that pathway be? And I can't predict that pathway, whether it will be something that will be more granular and modular, as we've talked about here, or whether it will involve large-scale plants that look like this one. But there is no reason, as we think about the fundamental energy efficiencies, which I indicated, the core elements of which are as efficient at small scale as large scale, that the primary requirements for this are simply, as Roger was pointing out, the availability of the excess renewable energy that will be required to drive such a process. So if we have that, I think we can at least see a pathway to megaton and gigaton scalability.
Okay, really, really interesting presentation, Harry. Thank you very much for joining us. So now, ladies and gentlemen, we're moving from seawater to shipping. Our next guest is Bo Seup Simonsen, and he'll speak about transitioning to green technologies in shipping. Bo is CEO at Maersk Mc-Kinney Møller's Center for Zero Carbon Shipping and also an advisory board member at CORC. Bo, please come and join us.
Thank you very much. Okay, thank you. It's wonderful to be here. I really love, maybe can we turn it down a little bit? To be in a community of the smartest people wanting to solve complex and relevant problems. And I think we've heard amazing examples today about people trying to do that. And I'm going to be talking about a challenge here which needs that kind of resource to progress. So imagine an industry that used to be called a hard-to-abate sector. It's an industry, the ocean shipping industry, that many know as a kind of a hidden industry. I think many think of it as being old-fashioned, maybe dirty, and hidden from the public. This industry used to be called a hard-to-abate sector, with the idea that obviously can't put a cable on a deep ocean ship. You can't use batteries to decarbonize it. So maybe it's just too difficult to get your arms around. And therefore, when IEA and COP and other global institutions set targets for the world to decarbonize, they thought of shipping as last in line, together with steel, together with concrete, together with aviation, and a number of others. But a lot has happened over the last years, and in the beginning of that transition, we established the Center for Zero Carbon Shipping, and we thought that we should use the tagline to say we need to show the world it's possible. And so this whole center came from a dream somebody had to say, we may be a hard-to-abate sector, but there's got to be a way that we can progress also and actually show that even if we are considered the hardest to abate, there is a way forward. By combining science, technology, policy, and financing mechanisms, there must be a way. So when we started out by trying just to get our arms around the problem, we can realize that shipping is critical infrastructure for the world. So any product, any piece of garment that you carry, or your car, or what you eat, has probably been on a ship. So shipping is a part of all supply chains, and it's critical, but you only realize when it breaks down, then all of a sudden those supply chains stop and we are in trouble. It's 100,000 ships operating globally. They burn 300 million tons of fuel per year, which gives about a gigaton of CO2 emissions, and that is about 3% of the global greenhouse gas emissions. So we're looking at a sector which is fairly small after all in terms of climate impact, but it is a part of all supply chains. So you can say in order for all the services and goods that we buy, in order for all of that to decarbonize, shipping needs to decarbonize and be part of the solution. And so shipping is in many ways a very fragmented industry. The 100,000 ships are distributed across the globe, thousands of ports, thousands of ship owners. The typical ship owner is not the Maersk, everybody here in Denmark knows Maersk, is not the Maersk size with 1,000 ships. The typical ship owner has 5 ships. So it's a lot of small owners distributed that are running the ships of this world. But there is a global regulatory mechanism in the International Maritime Organization. So in a very fragmented industry, there is still something holding it together and keeping the safety level high, keeping the environmental level under some level of control. So that's the industry we're looking at. And when we started the center at that time, we said there's a lot going on in our sphere, even if we call it a hard-to-abate sector. There's a lot going on in the world of science, there's a lot going on in the world of finance and business, and there's a lot going on the political scene, in the regulatory space. So how could a center contribute to such a world where a lot is already ongoing? Should you go deep in a specific area, or should you rather try to take the systemic approach and try to understand how do you mobilize a whole system? And actually, rather than just systems thinking, can we create a kind of systems action? So is there a way of making everybody move so that we avoid this chicken and egg type problem that we've talked about a few times today? So the center was established with that in mind, that a large foundation, the A.P. Møller Foundation, wanted to give a contribution to the ecosystem, not for a single business to benefit from that, but for the whole ecosystem to benefit from this. And the idea was to establish a collaboration platform that everybody could join, and that should be independent, so it would have no vested interest in any particular technology. Any particular country interest should be represented. It would purely be for the interest of the climate and the globe. It would need to be science-based, because there's so much vested interest in this world. There's so much political interest in this world. And the only way of arguing against that is to have solid data, solid scientific processes and methods to say what is truly benefiting the climate and the biodiversity in the long run. So that was really the idea of the center that I was fortunate to have been leading from the very beginning. And then it was also said that in order for this to really create mobilization, we need to get partners on board that are willing to lean in, put real resources to the table, and also put commitment to the table. So when we started implementing our strategy, we opened up for partners to become part of the center. And I considered this as one of the main risks in the beginning, that if we were not able to get any government offices or any companies on board, this would be sort of a very difficult thing to drive forward towards implementation. But I'm telling you, it was like drinking from a fire hose. So now we are 3 years down the line, and we have about 100 organizations, and now we have a number of universities that are connecting in partnerships as well. We have 100 organizations now from across the ecosystem. So it's energy producers and new types of energy producers, It is technology producers, fuel cells, combustion engines, batteries, etc. It is ports, it is ship owners and operators, and it is cargo owners, those that are paying for the ocean transportation. And then we have a category in the upper right corner, which is what we call the knowledge partners. So those are organizations that are putting a lot of data and insights and networks to the table, more than money, you can say. So I would say altogether we have established now a nice portfolio of partners. And when we run the projects now, we are including these partners in the project with the idea that we need to get partners on board that can help us understand what are the boundary conditions, the constraints, so to speak, in that wider system in order to develop solutions that contain both the technical aspects, the financial aspects, and the regulatory aspects for this to become implementable at scale. So let me explain a little bit about how we do that. But first of all, of course, it's about understanding the system and the scale and the timeline of the challenge we're looking at. So this graph here is showing you the emissions from shipping. As I said before, it's about 1 gigaton per year, coming from 300 million tons of fossil fuel being burned every year. This has been quite steady over the last 10, 15 years. Even if there has been like a 40% increase in global ocean transportation. And the reason for that is, of course, that the industry is adopting a lot of energy efficiency measures. So it has succeeded in decoupling growth from emissions. And of course, that's a good thing, but it will never take us to zero. So energy efficiency has brought shipping a long way, and it's now the most energy efficient mode of transportation you can think of. But it's, of course, still having an absolute emission. So going forward from here, as you can see on the graph here, we can expect the emissions from ocean transportation to grow as the world GDP grows, which of course stands in stark contrast to the Paris Agreement or the IPCC interpretation of that, to say that we need to get to zero by around 2050. So our industry is now looking at this huge widening gap and standing, I would say, at a threshold where the industry has realized that we need to be part of the solution, but we need to break that curve and start to decline very rapidly. So we now have set the 2030 mark as an important milestone. And when you look at the 2030 mark and we look at the IPCC, we need to make some really radical reductions of emissions. We can achieve, in the order of 45%. We can achieve a lot by energy efficiency. There's still a huge part of the fleet which is operating with old engines, with bad practices, with a lot of growth on their hulls, etc., etc. So a lot can be done just to adopt existing technologies. But it's not enough. We need to go further than that, and we need to start using fuels that have reduced climate impact. And the scale of this is pretty dramatic, actually, because if we said that we were to just adopt 5% of green fuels by 2030, that would be in the order of 50 million tons of methanol or ammonia. And 50 million tons is pretty much what we have in the pipeline today globally, for all other sectors as well. Power production in Asia, agriculture, etc. So we in our industry are also looking at this with concern and thinking, how can we get to the scale of these new fuels that we need? But there's a lot of positive things going on, and I'd like to just bring forward 3 examples here of ship owners that have now invested. So these ships are now being built, or they have been built, to run on new fuel types. So to the left, you have ship owners that are building ships which can run on methane that is decarbonized. They can run on liquefied natural gas today, and they are planning to shift to biomethane or electromethane. The middle one, that's a Japanese ship owner we're working with, is looking in the direction of ammonia, and many are now looking towards ammonia. And the last one is Maersk, and now have created a lot of follow ships, so a lot of companies are now building ships that can run on methanol. But of course, all of these, even if the ships can run on these new fuel types, are dependent on business systems that work, on regulatory systems that allow them to do it in ports and city environments, etc., where safety is a big concern. And of course, in reliable technology, so you can get insurance companies and so on and so forth to actually insure these extremely expensive assets. So what we really need in order to bring this new technology and these applied sciences to use at scale is, of course, to understand those systems that the engines and the ships are working in. And so a lot of our work goes into understanding this chain from the fuels to the ports, to the ships, and to the cargo owner. And you look at this, typically as engineers, we start to look at this from a technical perspective. Is it technically possible to do it? And so a lot of our focus in the beginning has been on just understanding if it's technically possible to decarbonize shipping. And here we can say tick, yes, it's technically possible. If we just look at technologies that are available today or that will be matured over the next 5 years, we can say, yes, we can decarbonize deep ocean shipping by new technologies. But then, like I said, you have to look at this also with the other lenses. And when you look at this with the regulatory lenses, you're looking at a rather complex landscape, because now you need to get authorities across the globe to allow to store new fuel types in the ports and city environments. You need to have new safety practices on board the ships, etc. So there's a huge piece of work to be done on the regulatory side. And finally, of course, on the commercial, financial side, it also needs to make sense. And here the thing is that these new solutions, they will be more expensive than the fossil-driven solution. There's no doubt about it. The cost of ocean transportation will go up by 20, 30, 40%, maybe even more in some cases. And if you look at that in isolation and say that this is now in competition with a fossil solution, in most markets, there wouldn't be a willingness to pay that green premium. That's just how it is. So you would find that even if you buy a pair of Snickers, Nike shoes or whatever, and you pay, $150 for those shoes, and the green premium is maybe 10 cents, when you look at the supply chain, there is no mechanism today to make that supply chain work. It's a paradox. If you buy an electric vehicle today, and the cost of that vehicle is $100,000, it'll probably be $1,000 to make that totally decarbonized as a product when it stands in your garage. But we cannot mobilize that supply chain, that value chain. So you cannot tick a box and pay $1,000 extra and get a decarbonized product. And that is a part of the challenge that we have to solve. So when we talk about system perspective, it's also very much the commercial system perspective. Because the underlying, I think, acknowledgement is that it is affordable, it is doable. It just needs to be fixed also from a commercial point of view. So the work we are doing, we've divided that into 4 areas. It's about elevating energy efficiency. It's about initiating what we call green corridors. So that's to get that new business system going. And we have a lot of nice examples of 7 places in the world where we're actually doing that. Right now we work a lot with Chile to produce new fuels in Chile, to export copper in Chile to the auto manufacturers in Asia so they can build green cars like I was just talking about. So that's initiating it, but it's still in very small scale. But then the 2 last ones are programs that will enable sustainable and scalable fuel supply. And it is about creating that demand at scale. And right now, to put it straight, I think our biggest chance in the world of shipping is that regulation will drive that scale of demand. So that's going very well, I would say. So this is how we have structured our work, and we have now about 60 projects that are distributed across these 4 programs, and we have all our many partners on board in showing the way forward on this collaboration platform. How deep are we in the science? If you look at this one here to the left, where you can say you go from building knowledge and insights to developing solutions, to planning and strategizing, and to implementing. And implementing on a country level is by making new legislation, new law that enforces this. And in a company, it is to actually do the investment and start running your business in a new way. Where is our center? I would say we are not the best when we are deep down. I would rely on universities to really go deep in the research. We are more in the 2 middle boxes there, where we're trying to understand, if you take it from the top, how would a country make a strategy now, for example, to combine climate and industrial and energy policies? What does that look like? And on a company side, how does an oil and gas company, how does a shipping company, how does a port make a transition strategy? What would a good transition strategy look like so that they can start investing? So that's the space we're working in those 2 middle boxes there, which is, of course, for us, extremely interesting. I wish I had more time, then I would talk a little more about some of these details, but I don't. Right? So I will just get here to the end and mention the green corridors as a very interesting example of getting the business going. So we have 7 projects going where we work across this chain from a technical point of view, from a business point of view, and from a regulatory point of view. And then we put all the stakeholders here together, so fuel production, ports and storage in the port and city environment. Then we have the ships and the ship designs, and we have the cargo owners. So for example, in Chile now, as you probably know, there's a lot of renewable energy in Chile. So we're looking at fuel production in Chile, how to upgrade some of the ports in Chile, how to build new ships that can export green ammonia or export green copper out of Chile. And finally, cargo owners that are willing to pay for this transportation. So an amazing way of understanding what is the implications, what does this new business system look like, what is needed in order to make it competitive, is to just try and do it. Put all the stakeholders together on this collaboration platform and say, let's try to visualize what this new system looks like. And in that also calculate, so what does it take to make this adoptable and scalable? So I think that's really how I think the headline here today was about accelerating the transition to scale and to adoption. And I would say that would be our best bet, is to get those stakeholders together and talk about how do we make this scalable from those 3 perspectives. Thank you very much.
Thank you, Bo. But we do have time for a quick question, so don't leave me yet. Clearly, the big challenge is to get enough, or one of them, there are many, is to get enough green energy to produce green fuels. And one from the audience asks whether the maritime sector will be able to compete with aviation and industry, for example, plastic, when it comes to carbon-based fuels in the longer run, because you're in this competition.
Yeah, okay, so carbon-based was mentioned, and that's a good point, because carbon is probably going to be, and maybe it already is, a scarce resource. So I think our working assumption is that that could very well happen. So we should try to identify sources of fuel for ocean shipping. that is, first of all, not in competition with existing grids that are decarbonizing onshore. So, for example, in US, in Europe, in Asia, etc., there's infrastructure, and any renewable energy connected to that infrastructure will probably be needed in the countries and the regions. And it is probably not a good idea for the bigger picture to use that energy on a large scale to decarbonize shipping. So we're trying to identify sources of energy and fuel that can power shipping and not take away decarbonization opportunities for places where it would be used more effectively. And that could, for example, be renewable energy out of South America, like I just mentioned, out of Africa, out of Australia, where there's an abundance of energy in the deserts, for example.
Will there be room for more than one alternative fuel? You mentioned ammonia, methanol.
Bio, yeah. I mean, I think the game is on, so to speak, and what we see.
But do you think there'll be one winner, or are you going with several fuels? I mean, because
not for many years, and the reason is that many of these fuels are produced in synergistic, symbiosis, if you will, with other processes. So depending on local context, it may be beneficial to use bio-waste in one area, and you can produce, let's say, biomethanol in one area, or biogas in another area, ammonia in a third area. And I would say they are competing, and I really believe they will for quite a long time. When we look at scalability, some of them are more easily scalable than others. But again, it depends on how these new technologies, like direct air capture, for example, how they evolve and how competitive they will be.
Yeah, and as you say, it's going to change the harbors a lot. Ammonia is highly toxic, so that's going to change, maybe also the political appetite for having them in the midst of the cities where some of the harbors is, and so on. But we're going to get back to this because you're joining us for the panel debate in the end, and we're discussing scale as well. And as you say, you are going to suck up a lot of the green energy. So we're trying to discuss how we can produce that later on. So you're joining us later, but thanks for now, Bo.
All right, thank you.
The last presentation before the panel debate also comes from the US. Holly Jean Buck is joining us from the University at Buffalo, where she is an assistant professor of environment and sustainability. And she will talk about one of the topics for the final debate, which is accelerating a de-risking social acceptance. So please, the floor is yours, Holly.
Thank you so much. It's a great pleasure to be here. I'm going to talk about social support for carbon tech, both carbon removal and carbon management. And I wanted to start out with this image from Third Way by Dr. Rudra Kapila and Dr. Simone Stewart and others, because they made an effort to try to picture what carbon management would look like in the landscape scale in a best-case future, which is rare. Not too many people are producing images like this. When we talk about CDR, we normally start with this graph, which most people in the public have not seen this graph, and they also don't know what it means to have several gigatons of carbon removal, what sort of infrastructure that implies. They also don't probably know what scale of infrastructure getting to below 2 degrees Celsius with our mitigation needs either, which is a big failing that I'll talk about. We've also heard a little bit from the State of CDR report. How are we doing with this? They looked at, around 2 gigatons of removals happening, but a very small amount of that being from novel methods. So what are these novel methods? We've seen schematics like this as well. In my experience, members of the public, when they see diagrams like this, they tend to read them as, let's pick the things that we like, rather than the message being, we have to do all of these things. Maybe we don't have to do all of them. but some of them are better than others, probably, and we're trying to figure it out. Governments like the US government are investing a lot of money in carbon management. We have about $12 billion of funding from the bipartisan infrastructure law, $3.5 billion of that going into direct air capture hubs. And you can see that the DOE tried to sort of, imagine the components of this. You see some things on this, such as, if I can go back, can I go back? I can only go forward, perhaps. That's okay. Yeah, small and minority-owned businesses, and direct air capture education, and, like a workforce development center, a STEM education for a community. They're trying to also put in the social infrastructure to this picture a little bit. So we're seeing kind of the first efforts to sketch that out as well, not just focus on the hard tech infrastructure. But everybody's wondering, will this work? Will we be able to build this out at the landscape scale? There are some warning signs. We've seen opposition both to different types of CCS projects, particularly in the Gulf South, in a region that's known as Cancer Alley along the Mississippi River. We've seen a lot of opposition in the Midwest to CO2 pipelines. And I want to step back and make a couple of points about how we think about technological scale-up. I think this quote from this recent popular book by the co-founder of DeepMind sums up a lot of mainstream thinking in tech about this. He writes that almost every foundational technology ever invented, from pickaxes to plows, pottery to photography, phones to planes, and everything in between, follows a single, seemingly immutable law. It gets cheaper and easier to use and ultimately proliferates far and wide. So in this book, he's really focusing on the wave driven both by AI and biotech. It's important to remember that a lot of investors and thinkers in CDR are coming from that kind of software or maybe biotech space. But this is very different than how sociologists would think about it, at least in the subfields that I work in. We talk about how technologies are socially shaped and that their dissemination is actually not inevitable. And I'm curious who in this room has heard of Chemergy? Not a familiar household term, right? So this is a whole field that was being developed in the late 30s, early 1940s. Basically, the idea is that new developments in chemistry were going to unlock the mass manufacture of things from biomass feedstock, bioproducts. And so this was kind of, in some ways, an alternative to petroleum. The factory triumphant is founded on field and forest. And even, you saw a political campaign. This was the person who was running against FDR, Roosevelt, putting forth Chemergy on the buttons, right? And so you see the material going from the fields into this kind of biorefinery situation and powering homes, planes, and cars. That was kind of the vision. You may wonder what happened to it. There's a lot of reasons why this field kind of died out, but one of the main ones was that petroleum was cheaper and the petroleum industry, nascent at that time, still was pretty well organized. But you saw some thinkers like this fellow, William Hale. He was a chemist who was really going around promoting this, doing field building, warning that storehouses of fossil fuels are precious endowments to man by nature. We shouldn't just use them indiscriminately. We should preserve them for our children. But already in 1939, it wasn't looking too great for this field, even though they had some top promoters like Henry Ford with his car that was actually manufactured out of soybeans, the different components. George Washington Carver, another leading figure here. And interestingly, one of the recent NSF grants earlier this year was a $20 million grant to researchers in Iowa that they're branding as 2.0, right? So we may have a revitalization of this field, but it definitely wasn't a linear thing. Like it didn't proliferate automatically like a wave. Another example, nuclear. We've seen that kind of come and go. We've seen shutdowns and a switch back to fossil fuels in a few different places, including New York State, where I live. A recent veto in Illinois, but then that was actually overturned last week. So there will be small modular reactors allowed in the state of Illinois. So back and forth, but again, not necessarily linear. And a big reason for this is culture, values. So both political economy and culture influence the adoption of new technologies in ways that are really hard to quantify and graph, but we can use qualitative methods to get at them. So I'll talk for a few minutes about what research so far tells us about the social acceptance of carbon technologies. You can see this common social science acceptance framework. I think this comes from a whole bunch of different studies. It's, nicely mapped here in one of the papers about carbon capture and storage. But you can see that there's different variables social scientists have mapped out: trust, fairness, affect, kind of emotion, how people perceive the problem, what the norms are, and that all kind of feeds into whether they accept this technology or not. So I'm not going to go through this and the body of literature that supports it, but I will touch on a couple of these things, including trust, fairness, and problem perception, which are all really important for carbon removal. So you might think that people support net zero, so won't they support carbon technologies? We have, a recent Eurobarometer study that shows that both in the EU and especially in Denmark, people agree with this statement. To what extent should we should reduce greenhouse gas emissions to a minimum while offsetting the remaining emissions, for instance, by increasing forested areas to make the EU economy climate neutral by 2050. So you can already see some of the challenges by the way they worded this, suggesting that increasing forests might be able to compensate for residual emissions. From a survey writer's point of view, I understand that they can't have made that clause longer by talking about industrial methods as well, because then the respondent would be reacting to the word industrial or technological and maybe lose sight of the original intention, which is to measure support for net zero. So surveys are tricky with capturing this. But you might read this and think, okay, we have social support for carbon management. Here's another example from the US. Even in the US, large shares of Americans want to take steps to address climate. They think it's important to develop alternative energy, although there is limited support for the idea of phasing out fossil fuels altogether. Most people support a mix of renewables and fossil fuels. And so you might read that and think, okay, well, probably then they support carbon management as well, because it implies, maybe some production of fossil fuels and then capturing CO2 or different sorts of infrastructures. But again, I don't think this is a given. They're supportive in theory. You can see polling for providing a tax credit to businesses for developing carbon capture and storage, which of course we have in the US. Both Republicans and Democrats were supportive of that. That did pass or become revised. And yet, what I see on the ground from qualitative research is actually bipartisan skepticism around both carbon removal and carbon capture, which generally are completely conflated in the public mind. So the social representations, meaning the mental models or the initial associations that people have around carbon management, include things like fracking, include nuclear waste, other types of waste storage, but also renewable energy in terms of something that comes and needs to scale quickly, air pollution. And so these are the things that people, if you introduce this idea, they look for things that they can, link it to make sense of it. And like this interviewee said, they made the comparison to fracking. is that good or is that bad? The respondent said, it's fine, but it sounds similar to fracking, which is supposed to be bad, so I'm not exactly sure why this is good, and that's bad. Maybe this is a message point that needs to be clarified as this goes forward. People are still kind of confused about how to place geologic storage into their mental schema. So I'll spend the rest of my minutes talking about why I think acceptance for carbon tech is different than thinking about social acceptance for other types of technologies. And part of it, these questions are definitely coming up with renewables and transmission and energy storage as well. Who benefits? Who bears the impacts? This is a schematic from Instagram, which I think is an important medium to follow to understand how publics are being introduced to this idea. It's a framework for spotting false climate solutions. And so it asks the viewer to ask these questions in order to evaluate potential climate solutions. Who's at the table and who's making decisions? Are the communities most impacted driving the solutions? Who is benefiting? Is it going to lead to further amassing of wealth and power for folks already hoarding wealth and power? Are there any unintended negative consequences? And how will this build or shift power? Will this solution disrupt or reinforce the white supremacist, patriarchal, settler, colonial, capitalist structures at the root of the climate crisis and interrelated crisis? Is it going to be liberatory and reparative for the communities impacted, et cetera? And so, this is, if you are maybe a younger person reading about false solutions, which is one of the main frames for carbon removal, as well as hydrogen and sometimes biomass, this is how you are invited to think by the media that you encounter. And these questions come up in the public sphere as well. So one example that people find when they search for information is this incident in Satarsha, Mississippi, maybe you heard about in 2020, where there was a pipeline breach. Many people went to the hospital from it. This gentleman lost consciousness. This family also lost consciousness, and there wasn't a good first responder response. There were a number of problems. You could read the report that the DOT put out. But basically, this is one of the first things people encounter. And so they're thinking about these questions about, who's impacted, what are the negative consequences. And so I'll give another example. This is from Livingston Parish in Louisiana. And the project here was by Air Products. It was the $4.5 billion blue hydrogen project that the local community pushed back on. They made a moratorium locally at the parish. That's like the commune level. The company sued because the lake that they wanted to inject the CO2 under was owned by the state of Louisiana. I won't tell the whole story of this, but basically you could see that the opposition was raised, and it affected not just this project, but other carbon projects in this area. The people raising it weren't necessarily the people who made kind of that Instagram about, settler colonialism and patriarchy. The people who raised the opposition at the site of storage were sportsmen and fisher people who were just concerned about the impact on the lake. Many of them work are familiar with the oil and gas industry, but just didn't think this project was a good idea. Belatedly, the company started to put up some billboards and try to showcase some efforts, but this has really affected the politics of all types of carbon projects in Louisiana. It's still moving forward. A recent earnings call from a few weeks ago indicated that, it's going to be more expensive, but they do intend to keep building it out. So you might wonder, well, even if there isn't social acceptance, does that really matter? But I think it does. I think the opponents here have succeeded in opposing other things, like a big petrochemical plant, which would have been a really polluting plant. So both frontline communities, now they have larger philanthropy making grants, backing them. They're pretty well organized. And their position on CCUS is kind of maybe summed up in this letter that many environmental justice organizations sent to the California Air Resources Board. California is another place where you see a lot of opposition. And their position is that CCUS is an extension of environmental racism because it increases environmental injustice for frontline communities. The communities who are bearing the burden are now going to bear the burden from CCUS. And they have sources like Mark Jacobson, Stanford professor, who's published peer-reviewed studies about how these technologies are not needed, right? So that informs their position. So you might wonder, okay, why is carbon tech seen as the same thing, basically, as these polluting petrochemical facilities? Well, that's because a lot of times it's the same actors behind these industrial projects, such as Exxon or Denbury or, Air Products. These are also the first projects people are hearing about, and sometimes the life cycle analysis on whether they're really carbon beneficial is not well spelled out. There's been very little community engagement. And so there's this question, do other types of carbon tech, putting microbes in the soil for enhanced weathering, or things that are really completely different from an operational and technical point of view, will they be seen within this overall basket of basically industry from the past? This isn't feeling like technology of the future to people. It's feeling like repeating what they've already seen. A few more things why I think this is different than clean tech. Lack of trust, but also no apparent scientific consensus that industrial approaches are needed for carbon removal, like I just mentioned with the work of Dr. Jacobson, but also this idea that if we reduce energy demand, then we don't need industrial carbon removal technologies. So this is very popular among some of the scientists in the EU. You can read this survey published in Nature Sustainability that shows kind of a preference for degrowth rather than green growth. And these are seen in a binary way. You also can see that because there hasn't been a good communications effort from the CCUS industry or from governments, frankly, people are filling in the information with production of their own facts and factual resources. So, according to carboncapturefacts.org, it's going to be expensive, dangerous, wasteful, unhealthy, unnecessary, a distraction. And finally, the last point I'll make briefly as I wrap up, there isn't a consensus on whether these new climate technologies are going to enhance freedom or constrain it. So freedom is an important value, not just in the US, but Europe as well. There's this big discourse now that, you're going to be forced to live in a pod, you're going to be forced to eat the bugs because of climate change. Climate lockdowns are coming, net zero is a death cult, the 15-minute city is going to be imposed on you. And this is kind of a new constellation, especially in the wake of COVID, and new political actors have formed in response to COVID. Now that that's died down, the same networks are picking up climate change. And it's not just a fringe movement, it's a political force, both in the US and in Europe, that's impacted, like the Dutch elections, for example, in the UK as well. So just a couple of points. I think the statistics about overall public attitudes are masking the attitudes of specific politically important groups. And it's not clear yet whether these groups see climate tech and carbon tech as part of that, as part of a new regime of surveillance and restriction, or as something that enables the things they like about their way of life. I'll skip this last one just to show a few more of the images and messages that you will encounter if you're just learning about this from social media. False solutions, industrial waste going to be dumped. And so in summary, we've increased investment in new tech, but we've had very little correspondent investment in the social infrastructure, in public engagement. Social acceptance is not a given, even from populations who are concerned about climate change as a whole, because of these concerns about benefits and burdens, because of the lack of trust, because of these debates around values and whether this technology is needed. awareness is growing, and at least in the US context, there's few visions of what green industrial processes might look like. So what do we do about this? Researchers can work with publics much earlier, even in the lab stage. Industry and researchers can also, consider the existing context in which these technologies are going to emerge for people. Think about if you can invent a different context for your work besides CCUS. We also need government funding on engagement for road mapping these trajectories, because right now the engagement comes when there's a specific project. People don't have the wider sense of the whole transition pathway in which that project fits into. And funders need to fund engagement that scales, so engaging the engagers, teachers, legislators, community-based organizations, local climate action planners, so that those trusted leaders can scale situated engagement where they are. There's no silver bullet here. It's like climate change. It's a very long, hard process of system transformation, and we have really been underinvesting in this part of it. So we'll wrap up there with one final image. Thanks so much.
Thanks a lot, Holly. Really interesting presentation, because we've spoken a lot about technology development today and scaling, but we cannot scale without public acceptance and without public support. So I guess it's a question of, the thing you spoke about, who reaps the benefits, is very at the core of these issues. So I guess you have to create some kind of local structures where the public can clearly see what is the benefit for our local society of this plant or whatever it may be. Do you have any suggestions as to how we can sort of handle this and make some, very clear structures where it's very clear what a local community is going to get out of this?
Yeah, so first I want to actually address the difference between social acceptance and social support. So I think you really do need benefits for social support. This technology is going to be a cost on society, and it's not enough if people just accept it. They actually have to want it. And so what sort of benefits can we think about? Usually if you ask people, which I've been doing in my research, what do you see as the benefits? They're kind of blank, because they're not used to, unfortunately, having industrial activity provide some kind of benefit. And because of the context of deindustrialization, right now we're in a context where people are competing to have any kind of permanent high-wage job, which means these local jurisdictions give tax breaks to companies that are going to come in. The traditional way you might find benefit is if you taxed that project, and they're in a situation where they can't do that. So as a substitute, what they're developing, and the Department of Energy set up some of this framework, is a community benefits plan, which works toward a community benefits agreement, which is an agreement between a project developer and some members of a community, not well-defined, who gets to represent that community. And those could be benefits that they negotiate, like funding for schools, for roads, for parks, whatever benefit they're looking for. But ultimately, it's a workaround, and I think maybe an ineffective one, to this problem of not being able to tax these facilities and get direct municipal income from them.
Mm-hmm. I promise we're going to speak much more about this in a minute in the debate. You just alluded to misinformation, greenwashing, and so on, and there's a question related to that. In an attempt to de-risk social acceptance, have you considered how we might navigate misinformation?
Well, I've considered this quite a bit. I'll try to think of how to make a short answer to it. So I actually think that misinformation is a problem, but it's not something you can cure by just promoting different content. Like, the frame of misinformation suggests that the problem is like bad content that circulates around. Really, the structure we have of our media ecosystem is that the structure itself is rotten at the core because it's promoting content that is more emotional, that evokes anger or fear. That's just how these algorithms are working. And unless we actually fix that, we can't fix the bad information that circulates. And so the remedies to that are really challenging. They involve education. They involve developing public platforms, social media platforms that are publicly owned. They involve a whole lot of things that are beyond the scope of what we are currently considering.
Yeah, and I guess it's a broader political issue as well. It's not only when it comes to implementing carbon technologies. Misinformation is a huge topic. We're not going to solve it today or tomorrow anyway. Holly, thanks a lot for your presentation. Just stay on stage because we are continuing with the panel debate, and I'd like to invite the participants on stage. You already met Bo Seop Simonsen, and then we have two other participants. One is Jarl Krausing. He's joining us from the think tank Concito, Deputy CEO and International Director. And the other one is Katja Grote Eberhardt, founder and CEO of Climate.co. Welcome.
Thank you.
The think tank Concito, I can say that Jarl is working for the green transition. Maybe you can fill us in there. It's a Danish think tank. And Climate.co, Katja, maybe just I should mention a few words about you. You are working with raising funds to carbon removal technologies. So you are from the financial part of the game, and you already met Holly and Bo. The question here is how do we bring innovative carbon technologies rapid to society? And clearly we have to discuss how do we accelerate social acceptance, sort of continuing where Holly left us a few minutes ago, but we have other things on the agenda as well, because Katja, you are here. We have to talk investment, finance, and regulations as well. So basically, barriers to adoption. You've followed us, followed the conference most of the day. Which barriers to adoption would you point to as the most important?
I think basically you need to get the narrative right. And I think much of the problem here is, and I feel like actually saying to Alfred, coming here to CORC, you always get wonderful lessons in chemistry and, the natural science of this. And it's that translation from natural science to social science, which of course is the problem here. In Concito, we've been working for several years, in terms of really the technical decarbonization of sectors, etc. And we just realized, there are a segment of people you simply don't reach. Not with the language that we have. And segment analysis show clearly that you have gatekeepers out there. No matter how we talk about climate, you will never reach them. So you need to exactly come back to the issue of values and define what is it that actually speaks to people. If you can't see the goal, why run? So what do you need to do to make people run? It is exactly to try and paint a future for them. What will the future be like? What is the benefit for it? We're actually on the threshold not of dealing with a problem, but actually creating a world that can actually provide a lot of solutions, not just on climate, but a bunch of co-benefits that comes with it. So I think really a lot of the issue here is we haven't had the right narrative when actually speaking to people. Another when we are talking about, concrete build-up of renewable energy on land, windmills or whatever, or CCS, which is coming now, but really also at the grand scale, what is the society that we want to bring? And we did some studies around that in the Nordic countries, which we can come back to.
Yeah, definitely. Yeah, because you made some interesting things there. As you can see, Anna is drawing the debate live. So that's really interesting to follow. So that's what's going on behind us. Katja, barriers to adoption seen from your perspective.
I think it's mainly around the sort of green claims we talked a little bit about earlier. So how do we ultimately adopt that we need to do carbon removal at scale? And we need the pioneering companies to actually do the first steps in making sure they reach that scale and reach a point of cost where it's also viable. So it's companies, it's governments, and it's everyone that basically adopts that carbon removal is something we need to acknowledge, and that is here to stay. And we can't really hide our way from it. And I think that's the biggest barriers to adoption from the point of view that we sit with. Of course, there's a bunch of other things. I know the rest of the panel, and when we talk about reduction of emissions, right? But the last point about removing excess emissions and removing, to some extent, also historic emissions, is still something that we need that general adoption. And we need to support the companies that actually make the right decision in this space. Yep. And you can talk about what's the right decision, and that's ultimately what we're trying to solve as well with sort of a comprehensive due diligence of the projects we work with.
Yeah. And I think we're going to get back to the investment issue, and maybe you, if you'll allow, Katja, I'll just begin with the social acceptance, and then you can just chip in whenever you feel like it, and then we'll get back to the finance and investment perspective, because you mentioned that you can soak up a lot of the green energy. And you mentioned Chile. This is not something we can solve in Europe or in the US. We have to reach out to countries in the global South. They don't have, necessarily very good experiences with the West coming and telling them exactly what to do and how to use their land. So to continue where Holly stopped, how do we reach out to these societies? How do we get decent cooperation with local government, local structures, so that they can see the benefit of having huge wind parks, solar panels, or whatever? I mean, the scale is enormous if we should support, for instance, shipping.
Absolutely, and I think our experience is, and I think this would probably apply to anybody, that no matter what is your entry into this conversation, into this agenda, you will find that this principle of just and equitable transition becomes very important. So I also very much liked your presentation. It was really good you brought this perspective in, because our experiences, and we came very much from a technical viewpoint to say, how is it technically possible to decarbonize? And then, of course, you realize that the regulatory and the financial aspect needs to go hand in hand with that. And so our journey was to say, okay, we can understand that, and then where do we get the energy? We need to get the energy from parts of the world that are not really involved very much in shipping today, except they buy shipping services. And then for this to become robust, those communities, they need to see the benefit, they need to see the meaning and the benefit in this. So now that we work in Chile, we have come to realize that it's down to the individual workers, it's down on people level, that the people in the local communities, they are concerned that new companies will now occupy the hospitals, that expats will occupy the schools, that the roads will be full of people doing all this fancy stuff with the climate. And but actually they had a pretty good life before all these people came in. So it's a net benefit case for the country, but down on individual level, it's not necessarily a net benefit case. So that has been an enormous learning for us, and I think we are very humble to this. So we work with companies and organizations that have this as their expertise. Now we go to Namibia, and we've just made an agreement with the ministries in Namibia, and we want to work in Namibia. But again, I mean, we are extremely humble to how to do this in a just and equitable, a truly sustainable way. Yeah. So I think our way of doing it is to find collaborative partners that that know how to do this.
Yeah, this is really interesting. But Jarl, how do we get, the benefits to reach locals? Because in some of the countries that Bo mentioned here, you don't have a lot of trust coming from local societies to governments. So just dealing with the government doesn't necessarily make life easier locally where these plants are being built. So, well, you said you've looked into it in Concito. Let's know. Let's get to know a bit about the conclusions.
Yeah, right now geopolitics is definitely playing, the wrong hand in actually building that level of trust between the global South and the global North. What we see definitely is also, even when engaging with the global South, outside negotiations, but also inside the climate negotiations, when you talk about building a net zero future, you right away start an injustice discussion. So you don't talk to African governments, for instance, about net zero futures. We're going to help you become net zero. No, you go there, and it's really much more an issue of talking about job creation, sustainable growth. It's about economic opportunities and new industries. That's the kind of, health benefits, what all kind of other societal benefits. That's what they get elected on if they have election. That is really the challenge, I think, also when we move into, for instance, also the CDR kind of agenda, which is right now featured a lot, or will be in negotiations. It's also being seen as, a bad excuse for not doing our part in the rich countries. So I think there's an extraordinary task in actually, making countries in the global south understand what the opportunities are and what role CDR can play in different kind of roles. But again, you're coming back to the same issue. You need the right narrative to get that buy-in and also demand-driven kind of a genuine partnership.
But how can you make it very clear to local communities that this is to the benefit of them?
You can build an economic model where actually part of the profit that you make from this installation actually remain in the community. And you see now, in new investments.
So not just for energy issues, for any issue.
Any issue.
Okay.
I mean, we've done it in different kind of development agenda for many years, that you actually build social infrastructures that have local benefits. And you could do the same here. There are already now investment pipelines going on where you actually keep part of the profit coming from these installations, keeping them in the society to support social work, building schools and that kind of stuff. And in a way, you can use the same model in a country like Denmark. I mean, we've been arguing for, now when we build up renewable energy installations, and out in the countryside, etc., keep part of the profit with the local community to exactly win that kind of support from
that's
the local
interesting.
population.
So, Holly, do you think it would be possible to make this kind of, well, maybe it's not co-ownership, but it's still, a sharing of some of the benefits, for football pitches, schools, anything. What do you think about it?
Well, so much where to start. I think that, one of the basic challenges with global development broadly is you have a situation where countries are exporting raw materials that are processed elsewhere, and you need to bring more of the value chain in country. That's one thing. I think a second thing is that you need to focus more on the worker and the labor perspectives. So if you want to do, for example, enhanced rock weathering in Malaysia, and the workforce there is often females spreading the fertilizer on these fields by hand, then you're putting that burden on this female underpaid workforce. How do you also transition those jobs in this new context of this new income stream so that they're better jobs? Can you think about worker and collaborative models instead of just like a big contract with a foreign corporation? I'll leave it there, but a lot to say.
But Holly, how important is this issue?
It's critical if you want to get it done. I think the one main thing that countries could do to create some goodwill and legitimacy is develop specifications around residual emissions. So if you say, residual emissions are reserved for these truly hard to abate activities, then you don't get into this situation where you're asking another country to use up their carbon removal capacity to compensate for your maybe wasteful luxury emissions. That's one policy step that I think is necessary for this all to work.
Yeah. Well, how do you work with this issue? Because, you're very much focused on shipping, but this is very different.
No, absolutely. This is land-based infrastructure development with a clear link to the local communities. So we use the model I showed here. We use our collaboration platform. We developed the blueprint for how to develop these green corridors. And then we collaborated with the World Bank, with Global Compact, with some of the local communities to develop guidelines for how actually to create the narrative. You can say, what are sort of the objectives and the boundary conditions that you need to be aware of when you start to go into these development plans. So that's the principles we are using in Chile now. And we, of course, they are growing, they are maturing as we apply them and as we invite new stakeholder groups in. that look at these from different perspectives. I mean, just an example. We were in a meeting and somebody said this will definitely lead to a lot of maintenance workplaces. And the local governor said, that's fine, but I want universities and R&D. And of course, that kind of conversations brings a lot of granularity and perspective to what we're looking at, and also, how different perceptions. I mean, some of the conversations are very immature, so there is something about collaborating and sharing knowledge across that's going to be very important.
Yeah.
Because we are at global scale, right? So it can be multi-regional, but there is a value in sharing that knowledge across.
Yeah, I think it's very, very interesting, Holly. You said that carbon tax is seen as the same thing as petrochemicals. So there is, maybe you have something related to that. There's a great trust gap. We need to build some trust there. Because there's no free ticket, even though you're working for the green transition.
Yeah. No, and I think that's why you would also see one of the key messages from the UNEP's emission gap report is exactly the point that our friend from Caltech actually pointed towards. You need to build credibility in how we work and manage CDR. No matter what technology is, you need to build that very strong MRV, so people actually can see there's a strong knowledge base for what you have. But then in terms of, working with the mistrust, it's also, getting the data right in terms of what are the risks locally when you apply, whether you're CCS on the ground under your village or whatever it is. We need that evidence base, and that also points towards the need for deployment to get exactly that kind of learning as it is now. The problem is time and scale.
Yep.
So there is, I think, a role for governments really to engage in that dialogue. Also in Denmark, we have movements now coming together that goes against the CCS. Even if we have a broad, actually, kind of acceptance so far, it will come, no doubt.
Yeah, and land mills as well.
Land mills as well.
Yeah. Okay. So let's leave the societal acceptance for a moment and turn our attention to investment, Katja, because you are joining us too. Clearly, investment is a barrier too. When we spoke earlier, you said we need carbon removal credits in this part of the world as well. Can you develop a bit on that?
Yeah, but I also just wanted to comment on what you said before, because what we often talk about is carbon removal is one of the biggest industries we have to build in the shortest amount of time, and that goes for one part, that's carbon removal. Then we talk about everything we do on the renewable energy side and everything else. And that means that we are laying the foundation as we're basically finding the solutions. So we have to trust that everyone brings the quality and the requirements into that specific sort of overview, and that we're all following the same direction. But overall, it's about collaboration, as you also say, and how do we actually make sure that everything we do is pointing in that direction, while we have a clock that is very, very fast ticking above our heads, right? And that's exactly what we also went into this market with, because it's not an easy market to operate in, and especially when we're building up an industry from scratch. So one thing is that we need to get investing and financing into to the space. We also had Climeworks here as a company today, and you can tell that the amazing technologies that they're building also relies upon scale and funds sort of going into that development. So it's one of the most crucial aspects of developing out the technologies. And then on the side of that comes the social acceptance, the surrounding societies around the tech and the projects that we actually sort of build up, the regulation that comes with it. How does the companies and the industry adopt this? How do we actually move it ahead? I see very many similarities to renewable energy in the way that we see responsible companies actually driving the transition forward and sort of making those you can say commitments, early stage commitments into carbon removal technologies. But it is a full industry that needs to be developed. So once we have that commitment, we need to have insurance in place. Then we need to get the financing in place. And then we need to get everything ready for monitoring the deliveries of the project. So I would just say I very much agree with everything we talk about here, but there's a lot of aspects around this.
Yeah.
I agree entirely on the need for a negative crediting system. There's actually an effort underway to build a model that will actually propose you do that in the European carbon market, together with a bunch of European think tanks. Hopefully we will come up with a system to exactly create that kind of pull factor for financing that kind of thing. But I also find you need different kinds of investment instruments, right? I mean, you have that granular kind of technologies, they're small ticket size, so you need microfinance that kind of work in that system, to get that on. And then you need, of course, large scale, the big ticket kind of stuff. And that's why you think we stand with a particular issue that we know also from renewable energy, and I'm looking down at you, Anna, somewhere, asymmetry. There's symmetry challenges. Who will take the risk of building these kind of huge installations? The benefits will be for other countries to reap, but some government, here the Danish government, will actually take that, risk. And is that fair? You need a model to distribute the risk upfront. That asymmetry, there's a big problem.
And I guess, Bo, you are dependent on a part of that system as well. As I said beforehand, green energy, electrolyzers, PTX processes, something that the shipping industry is not directly responsible for. But you do have a lot of investments in your side of the sea, so to speak, because you make heavy investments in ships. Where do you think the investment issue is most critical for you? And do you see a larger appetite for investing in green technologies on your side of the table?
So, the shipping industry, now I'm not from Maersk.
No, I know.
Just remember to remove that little blue thing.
Yes, it's true. It carries the founder's name, though.
Because I'm not speaking for Maersk here, but what is happening right now is that here's an industry that has been used to buying its energy on a commodity market, and that's no longer the case. If you want green fuel today, you need to work with projects that have 15-year time horizon on the investment, and you need to commit to that. And that's too much of a risk for most of the ship owners today, or basically for anybody. That is just an enormous commitment. And the industry is not geared for doing that. So some mechanisms need to come into our industry, and we rely on really smart people like Jarl here to crack that nut, because we need some instruments. And we've seen now Anders is down now. I mean, we've seen some genius instruments being implemented from the public side, contracts for differences, etc., that have taken out marginal risk so that investors can come in and confidently invest in that land-based infrastructure. So we get the scale of that with a little bit of engagement from public side, and we believe that's going to be necessary in this transition phase now over the next 10, 15 years. And we have ideas about how to do that, and one of the obvious ideas which is being discussed in the International Maritime Organization is to put a carbon tax, if you will, a carbon price, collected through the fuels. You collect that money, and then you not only punish, so it's not only a punishment to the fossil consumers, but you also collect that revenue and give it to the first movers that are actually investing in good new green technologies, and that model can be applied widely. I hope you agree.
No, I do. I mean, and it's the hope of many in the climate environment that it will be established. I think then all the argument comes around: how should that money be spent? Is it the loss and damage fund? How much should go back to the greening the industry and so on? But I think the idea has a lot of general support, in terms of at least in some countries. I wouldn't say everybody
no, but it's also China, like when you look at the EU system now, for example, they implement now an ETS system, and that money apparently goes into one big box.
Yes.
And it doesn't go back. I mean, we would love some of that money to go back to our industry so that we can start actually to get going.
Yes.
But that's not necessarily how it's going. And I think that's also how many countries are looking at taxes, that they are not earmarked. No. They come into the big box and then they used and that's a little bit of a difficulty actually for us. So I think on the public side, we need some innovation to stimulate these kinds of innovations.
Yeah. And Bo, I hope you realize that the blue star disappeared from your name live. Oh, it's gone.
Oh, well done.
Okay. Holly, speaking of barriers, we've spoken about regulation earlier today. Carbon tax is definitely on the agenda anyway in the Danish political environment. To what extent do you think regulation pushes public opinion and provides a sort of framework in which the public opinion develops? Do you know what I mean? Or do you understand what I mean?
I mean, the way I come to that question is through thinking about regulation for safety. So, for example, in the US, we have this Class 6 well drilling framework from the EPA to regulate the safety of geologic storage. We have an agency, PHMSA, within the Department of Transportation that's working on a rulemaking about CO2 pipelines. And so I think what we need to do is increase the staffing at those programs, increase the speed at which they can move via increasing the staffing, and that has a bearing on public acceptance. If people think this is actually well-regulated, safely regulated, they're more likely to accept it.
Yeah. Do we know if Jarl just addressed the fact that even in Denmark we do have quite a lot of resistance to these projects. Does this resistance go for most of the countries all over the world, or does it very much depend on whether there's a social acceptance of climate change and the fact that we all have to chip in and do something about it?
Yeah, I mean, generally we don't have good data for the whole world. This is a problem within social science and maybe climate science more broadly. What we do know is that if you talk about it in the abstract versus something near your home, that definitely decreases acceptance. There tend to be age and gender differences in terms of acceptance. Mm-hmm. So there's definitely variability between countries, but there are those general patterns as well.
Yeah. Okay, Katja, before taking just a few questions from the audience, how do we scale the investments? Yeah, scale is word of the day.
Yeah. Well, I think what we work very much with is companies that are on a net zero journey. So they've made a commitment, it could be through Science-Based Target Initiative or other initiatives, and they're removing their residual emissions, their unavoidable emissions. Generally, that's around 10% of their total emissions, having sort of made a reduction plan. And those commitments are right now being discussed in the next, let's say, 10 to 15 to 20 years out, because it's going to be a big game about carbon asset management, really, for these companies to meet those commitments, so it's not just another commitment that falls short. But we need companies to realize that to actually be able to prepare for 2030, which many have in scope, they need to start now. So that's going to be a big driver of the early investments going into the projects and the big investments that are actually needed and the ones that we're already seeing being made now. But we need more of those. And I would also say we need more public commitments, like we saw in the US with the Energy Department. And I think that would be driving a lot of that also public interest in the space.
Yeah, so more carrot, and maybe some stick as well, but the US carrot is interesting. Okay, I have a few questions coming from the audience. I think this one may be to you, Holly. Some research also shows that shame, fear, and pressure motivates acceptance and action for parts of the public, but what direction should we take?
Yeah, actually...
Speaking of carrot and stick...
This literature is actually really mixed.
Okay.
You can find studies arguing both ways for it. My personal opinion is that hope and optimism are better motivators, and right now our problem is that people don't have any optimistic vision, whether it be about carbon removal or industry or confronting climate change. And like you said about the narratives, we need some narratives that seem credible around the place of carbon removal within this transition.
Okay, and we've got one for you, Botu. I think that goes back to your presentation. Can you elaborate on ammonia versus methanol in terms of the climate impacts?
Yes. One of the key elements that the industry is working on is to get sound, solid life cycle standards, which will enable, a lot of innovation because the different technologies and the different fuels will be assessed according to the true systemic impact. And particularly ammonia and methanol are being discussed a lot because they have potential in different ways. Ammonia is clearly scalable because there's easy access to nitrogen. So if you have hydrogen, either green hydrogen from some green source of electricity or blue hydrogen from carbon capture and storage technologies, then you can produce ammonia at scale. Methanol relies on access to carbon, and climate neutral or carbon is difficult to get your hands on. So direct air capture is still very expensive, and biogenic carbon is limited in resource. So on the other hand, methanol is very easy to use as a fuel. It's almost like gasoline or diesel oil in terms of handling and combustion properties and so on. So a lot of shipping companies, they are now turning to methanol for that reason. They believe that they can buy a certain amount over the next 10 years, and they probably can. But it, depending on, and I think many of them are now realizing it's not that simple to get a methanol which is reduced to, let's say, reduced by 70, 80 or 90% of the climate impact of fossil fuel. It's difficult to get your hands on that. So the competition will be on now to really get access to scales of fuel. So that's how, on the other hand, ammonia is not approved yet from a regulatory point of view. There are some safety elements that need to be approved. Both storing it in cities is difficult, and also taking it on board the ship. So that's how those two are competing.
Okay, really interesting. We're coming to an end now. Katja, Jarl, Bo and Holly, it's been a great pleasure having you here in Copenhagen discussing these important issues. Thank you.
Thank you. Okay.
All right, ladies and gentlemen, we are slowly coming to an end. And as you have all seen, Anna Leborn has worked intensively on trying to draw this debate, which is all right, this debate, Katja. So, sorry, Anna. So please come and join me. And, you need this table, right? Because there's some electronics that needs to go into the plug. And then you can take us through what's on your iPad.
Okay.
All right.
All right.
There we are.
There we are. Now we can zoom. So thanks for a big challenge over here in the corner. I'll just briefly go through whatever input I managed to capture from each of the panelists. So you were asking firstly about barriers for adoption, where Katja said that reaching scale is important. Carbon removal is here to stay, and we need to acknowledge that. We also, Jarl talked about the translation from science is important, and it's important to find out what, in motivating people, what values make people run, what benefit can they run for.
Exactly.
And we talked about communicating net zero goals for people that is not a benefit to run for, because that is not near enough. So you need to talk about job creation, new industries, so local benefits that make people buy in. And just is very important. Country and individual levels can be different, and this is Bo.
Oh, yeah.
Talking about the communities delivering fuel. They need to find collaborative partners that know how to do it, and engage the local communities in developing these guidelines and sharing knowledge across. And Holly was talking about the aspects of different raw materials, the use of them, the local workforce. Who is it actually? The ones that need to make these raw materials, and to how can we make collaborative models? Acceptance is important. If you can say this is well regulated, then you will have acceptance among people. And abstract versus near. People go for what is near. And then we talked a little bit about regulation, carbon removal, trust and common direction. Regulation, insurance, finance and monitoring needs to be in place. And Katja also talked about, everybody needs to start now to prepare for 2030, and we need more public commitments. Mm-hmm. Last words I got from Jarl was that we need to build the credibility, and we need a model to distribute the risk among partners. Carbon tax model will be implemented. It's a matter of finding out how and when, and also discussing where should the money go to. Four final comments that I got was there is an enormous risk, and he was also addressing this model needed to distribute and work with that. Otherwise, the shipping companies cannot take that risk alone. And then we were just elaborating on the pros and cons of ammonia and methanol. You asked about the shame and fear as motivation. No. And
Holly didn't buy that one.
Yes.
No.
So we can
okay, Anna, it's been absolutely a great pleasure and good fun to follow your work. So thanks a lot for joining us today.
Thank you so much.
And now I'm going to hand over the floor to Alfred Spormann and Marta for a few concluding remarks here on stage.
Thank you so much, Nina, and thank you, everyone. Wow, what an afternoon. We probably all didn't imagine we would hear that much really high-level information, and I hope, similar as I did, you learned something new, you got inspired to think about new areas that you haven't thought of. I hope you get moved out of your comfort zone to think in a certain way and adapt also information and knowledge where you don't have an answer how it fits to your own project, but it actually is an important part in the entire discussion that we have. So I really hope that you feel inspired, and thank you for coming. One thing I want to do before we close is, can the entire CORC staff please come forward, or if you sit down and stand up, please. I want to acknowledge all the people who did actually the work to come forward, please. So we have Preston, Tina Fruland, who really pulled this entire thing off and organized an amazing part. We have Mats Bendiksen, Stephanie Christian, Rebecca Bastaran, Nicole Mattis, Sylvia Zieger, and Tina Madden, who really pulled this entire thing together. And knowing it from the other side, it was immense what went into this in terms of logistics and planning this, making sure that the speakers actually were prepared, arrived all in time. Thank you all for coming, because we wouldn't have known what we would have done without the speakers and the panelists. So give a big round of applause to our staff. And finally, I want to thank you all again for coming, and I want to ask all speakers and panelists to come up to the stage, because we're taking a final group picture. So thanks again, and I hope to see you next time around the same time of the year.